Good afternoon. It is a pleasure to open this online section. The real opening will be tomorrow in the presence event, but it is nice to see all connected here, and it is a real pleasure to meet you in presence, of course online. I want to thank you for the participation. In this conference, we have a lot of participants from 42 countries, which is quite a good success for us as IGF. And we would like to thank all of you for the kind support that you are giving to our society. I hope that the discussion of this conference will be really fruitful, and we will make a state of the art of recent studies on the topic of fracture, fatigue, and structural integrity. So I would like to open this conference, and I will give the floor to the chair of this, to the chairman of this section. Thank you so much.
Thank you, Filippo. My name is Vittorio Di Cocco from Cassino University, Italy, and I would like to remember some rule of this session. We have 10 minutes for each presentation. Please spend 7 or 8 minutes for the presentation and 2 minutes for the discussion. So please stay in the time, and we can start with the first presentation. The title is In Service Degradation of Rolled Carbon Steels, the Role of Damaging, presented by Professor Nicky Forchin. Please.
Yes, thank you very much, Mr. Chairman, for the introduction. It's all good, yes?
Yes.
My presentation is seniors.
Yes.
So, thank you very much. There is a presentation outline, and the first topic of our presentation, general irregularities of operational degradation of structural steels. It is well known that long-term operation causes in general a degradation of mechanical properties of structural materials, including steels, in comparison with as received state. A long-term static loading, as a rule, is dangerous under the action of aggressive environments, but regarding cyclic loading, it is especially strong factor for steel degradation. These aspects are superimposed on the features of operational degradation of rolled steels. Let us start with the scheme, which shows two main stages of in-service degradation of structural steels. The first one is the formation agent, and the second stage, damage accumulation, which is more dangerous. This slide demonstrates sensitivity of the different parameters of brittle fracture resistance, namely impact strength and fracture toughness, to operational degradation. Fracture toughness is more sensitive to degradation than impact strength. Concerning the impact stress, test energy for crack initiation is slightly sensitive to degradation, and energy of crack propagation is more sensitive. Usually, characteristics of plasticity are not enough sensitive for evaluation of operational degradation. However, their sensitivity can be increased if to compare unoperated and operated states of steel after preliminary hydrogenation of specimen before tension. Here we notice that fracture toughness is the most sensitive for evaluation of operational degradation. Concerning the parameters of fatigue regrowth resistance, we should separately consider pre-threshold region and the middle part of region. In the first case, we have to take into consideration crack closure effect, since usually operation causes an increased crack closure effect. Regarding a middle part of fatigue regrowth in air, it is less sensitive to operational degradation, However, corrosion environment will increase fatigue regrowth rate more intensively for exploited steels. An increase of stress ratio increases sensitivity of fatigue regrowth rate to operational degradation. The second topic concerns operational damaging as the main factor of in-service degradation of rolled steels. On this slide, you can see operational damaging on fracture surface after Sharpie test. Formation of big circle pores in rolling direction evident due to high pressure hydrogen. This process should be easy in lower strength steels, while high strength steels are sensitive to damaging due rather the cohesion mechanism of hydrogen embrittlement. So steels in wide range of strengths can be sensitive to hydrogen-induced damaging, but due the different mechanism. The final topic, peculiarities of the experimental status of in-service degradation of rolled steels under cyclic loading. First of all, it should be drawn that in generally opposite effect of impact strength on fatigue strength and smooth specimens and brittle fracture resistance like impact strength and fracture toughness. Fatigue limit detects rather crack initiation resistance, while impact strength and fracture toughness detect crack growth resistance. It is principally important to understand the different role of strength and damaging in the process degradation. So, concerning operational degradation of a change of fatigue strength will repeat unambiguous change of strength detected in two stages as usually of degradation. Since cyclic loading is stronger factor of damaging than static loading, we should expect early start of the stage of damaging in comparison with static loading. The philosophy of such approach is shown on the bright example of sea portal crane, researched about 40 years in the condition of long-term cyclic loading. A level of degradation in the roll plate still was dependent on the level of operational stresses. And pardon. And on this slide, you can see dependence of impact strength. Impact strength separately of longitudinal and transverse specimens on the calculated level of operational stresses. More level of stresses, less level of impact strength. Revealed essential differences in impact strength of longitudinal and transverse specimen is caused by development during service delamination in rolling direction. It was confirmed by macro and micro fractography of specimen. And concluding remarks, thank you for your attention. And finally, it is information about the conference devoted just damaging in materials, which will take place in Ukraine this year under the AC's auspice, also in hybrid mode. I would like to invite you to participate in this conference. Thank you very much again.
Thank you very much, Professor Nikiforchin. Any question from the audience? No one? Just a curiosity, the damage along the interface in a longitudinal way could be due to the accumulation of hydrogen at the boundary of the grains, or not?
It is, of course, if hydrogen transported, it is easier way for him on grain boundaries. It is the classics, yes. However, even in this hydrogen can affect only inside in grains, since, for example, fracture toughness. Fracture toughness usually fracture is not a great boundary bond across grain, and this detects such effects of degradation. Even therefore, to our opinion, not is it so big measure, maybe less measure by hydrogen effect also in transgranular fracture, since, for example, for low strength steels, you have possibility to see cell pores about half of a millimeter. It is only can be formed only under hydrogen pressure, but especially in low strength steels, where stress is caused by hydrogen is comparative with strength of materials. For high strength steels, this mechanism is not so less. Rather, the cohesion mechanism, as a typical mechanism of hydrogen abrical, is typical for high strength steels, but for low strength steels, especially in rolling direction between for example, matters and inclusions, so-called, and these pores can be formed rolled in rolling direction, rolled of such big pores, big defect. So our opinion is high pressure hydrogen. So hydrogen, this roll is not grain boundary. This is a long direction. So.
Oh, thank you, Professor Nikiforchin. Thank you for your presentation. So let's move to next presentation. The title is Development of a Finite Element Model for Optimization of the Bone Fixator Design, presented by Professor Pham. Is here?
Pham is not here. I will be a presenter. I'm
okay. Great.
Yes.
Please.
Okay, can you see the presentation?
Yes, it's okay.
Okay. So, good afternoon, ladies and gentlemen. My name is Oleksiy Mohun. I am a student of the National Technical University of Ukraine, Ihosikorsky Kyiv Polytechnic Institute, and the topic of my report is the development of a finite element model for optimization, the bone fixator design. In the case of gunshot injuries to bones, the primary method of surgical treatment is osteosynthesis with the help of an external fixation device or an X-fix device. The advantages of fixation with this device are ease of wound care, patient mobility, reduction of hospital stay, and relative ease of installation, which is why X-fix device is also used in field surgery. In Ukraine, it has become significantly widely used due to a significant number of wounded people who need to quickly immobilize a broken bone for transportation to medical care facilities. But installing X-fix device according to the scheme used for simple non-catchment bone fractures is unacceptable, since the rods located near the fracture site will enter the bone tissue, which has changed in biomechanical characteristics, which are caused by the formation of the zone of shock wave osteoporosis and linearly decrease with increasing distance from the defect. Therefore, alternative location of rods were proposed. 4 options for placing the rods of the researched model were considered: a standard location, in other words, the internal rods are located at a distance of 40 millimeters from the fracture zone, a scheme with remote inner rods, a scheme with inner rods located at an angle of 75 degrees to the axis of the bone, and a scheme with inner rods located at an angle 60 degrees to the axis of the bone. Conducting experiments to determine the stiffness of systems is difficult and time-consuming. Therefore, modeling of the deformation processes of the tibia external fixation device systems with various options for the placement of the rods was carried out using modern computer tools using CAD, CAE methods to access the stress-strain state of the biomechanical system. Therefore, our object of research is the system tibia XX device. System modeling was carried out in the SolidWorks software package. Since our goal is to simplify calculations as much as possible in the first approximation, we considered two setups of the system, so tibia and rods. The tibia system is a solid 3D model of the real bone XFix device system using a bone model. The rods model is also a solid 3D model, but with the use of metal rods instead of bone, since creating a bone model is a quite time-consuming process. Let's proceed to the numerical simulation of the stress-strain state of the bone XFix device system by the finite element method. For this, the ANSYS workbench software complex was used. At the stage of pre-processing, we have to perform several actions. At first, we will consider the tibia system with 4 options for the placement of rods in compression. Firstly, we import our models into the ANSYS workbench software environment. Secondly, we set the properties of the materials. In our case, it's a medical steel and cortical bone. Thirdly, we create a finite element mesh. That is, we divide our object in a certain number of elements, forming a discrete model for which we set boundary conditions. After discretization, we have models consisting of solid 186 and solid 187 elements. After that, we set the boundary conditions for our discrete models. Therefore, for all types of load, we apply a force of 10 newtons, fixed support, and in the case of torsion, a remote displacement. Since we're interested in the displacement of points of the system, in solution section, we choose total deformation, which will show the displacement of nodes of the discrete model. After that, we start the calculation. After calculations, we receive the desired results of the displacements. We carry out the similar actions for systems in bending in the plane of placement of the rods. For systems in bending perpendicular to the plane of placement of the rods. And for systems in torsion. From the obtained displacement results, we find the stiffness of the system by dividing the applied force by the largest displacement. Next, we compare the stiffness of the systems. After analyzing the results, we can conclude that the location of the internal rods at an angle to the axis of the bone, namely at an angle of 60 degrees, makes our system bone XFix device more stiff, and therefore the displacement of parts of the broken bone relative to each other under loads will be smaller, which will speed up the patient's recovery period. Let's move on to the second part of the problem, namely the comparison of the system with the real bone model and the simplified model with rods. For the rod system, we perform similar actions, namely setting the material properties, creating a finite element mesh, setting boundary conditions, and performing calculations. As in simple, consider the deformation of systems during compression. So here and here. After receiving the calculation results, we compare the stiffness of the systems. From this, we can conclude that for approximate calculations, it is possible to use a simplified model with rods, since the error of the results doesn't exceed 10%, while the number of nodes in the discrete models are, in the tibia model, 1,400,000, and in the rods model, approximately 300,000. So thank you for attention, and I will be happy to answer your question.
Thank you, Alexei. Any question? No one? Just a question. How do you modelize the hole inside the tibia bone?
our model of bone was not so detailed. We just have scan machine in the university, and we have a real bone. So we just made it from the cloud of dots and did this 3D model. So it's doesn't even empty inside, but we just set the properties that this bone is not empty.
Okay.
So yes, and it's a cortical bone.
I think the results are very close to reality in case of torsion and bending. Not so much in case of the shear, because the maximum load is inside the bone in this case. So, okay. Any question from the audience? No one? So let's move to next presentation. The title is Fracture Study of Inhomogeneous Viscoelastic Beam with Longitudinal Cracks under Axial Force and Bending Moment. The presenter is here.
Yes. Hello.
Professor Rizzo, hello.
Yes. I am going to share the screen. Okay.
Professor Rizzo, we are seeing your Zoom page. I think
yes, I'm trying to share.
presentation.
Okay, one moment. I'm trying to share my screen, but
Yeah, it's shared. Okay.
okay.
Oh, thank you. Thank you. It's all right. Okay.
Okay. The title of the present paper is Fracture Study of Inhomogeneous Viscoelastic Beam with longitudinal cracks under axial force and bending moment. The present paper studies
the screen is not shared in this way. We prefer the last one modality.
Okay, one moment. Now, can you see the screen?
We see nothing.
Well, nothing.
It's gray.
Okay. I will try again. I'm sorry for this situation, but something with the computer here. Can you see now? Can you see now the?
Perfect. Okay, it's okay.
Okay. The present paper studies the inhomogeneous viscoelastic beam structure with 3 longitudinal circular cylindrical cracks shown in figure 1. The beam has a circular cross-section of radius R4. The length of the beam is L. The beam is clamped in its right hand end. And the loading consists of an axial force and a bending moment applied at the free end of the beam. The cracks 1, 2, and 3 are circular cylindrical surfaces. The beam exhibits continuous material inhomogeneity in a radial direction. The material of the beam has non-linear viscoelastic behavior that is treated by using the stress-strain relation, formula number 1. The distribution of the material property B that is involved in this relation in radial direction is expressed by formula number 2. The longitudinal fracture of the beam is analyzed in terms of the strain energy release rate by considering the balance of the energy by formula number 3. After some mathematical transformations, one obtains formula number 5 for the strain energy release rate. The longitudinal displacement and the angle of rotation of the free end of the beam are obtained by applying formulas number 6 and 7. The strain and the curvature are obtained from equations number 8. The distributions of strains are found by formulas number 9. The stresses are found by substituting of strains in equation number 1. Then by substituting of formulas 1, 2, and 9 in formula 8, one obtains equations 10 and 11. The strain and the curvature are obtained from equations number 13 and 14. Finally, the strain and the curvature of the uncracked beam portion are obtained by using equations number 16 and 17. The strain energy that is involved of the solution for the strain energy release rate, the strain energy is found by using equations number 18 and 19. By integrating a stress-strain relation, this is formula number 1, the strain energy density in crack arm 1 is obtained by formula number 20. The strain energy is expressed by formulas 21, 22, and 23. Then, by substituting of strain energies in formula number 5, one derives formula number 24 for calculation of the strain energy release rate. The strain energy release rate is derived also by using formula number 25 for control of the solution. The complementary strain energy density is found by using formulas number 26 and 27. Then by substituting of the complementary strain energy in expression 25, one obtains formulas 28, 29, and 30 for calculation of the strain energy release rate. The solutions derived are used to evaluate the influence of various factors on the strain energy release rate. For this purpose, calculations of the strain energy release rate are performed. First, the influence of material inhomogeneity is illustrated in figure number 2. It can be observed in figure number 2 that the strain energy release rate decreases with increasing of the parameter Q. In order to evaluate the effect of the location of crack 1 in radial direction, the strain energy release rate is plotted against R1 to R4 ratio in figure number 3. Figure number 3. One can observe in this figure that the strain energy release rate decreases with increasing of R1 to R4 ratio. The curves in figure 3 indicate also that the material nonlinearity leads to increase of the strain energy release rate. It can be observed in figure number 4 that the strain energy release rate decreases with increasing of the value of the parameter H. Increase of the radius R4 leads also to decrease of the strain energy release rate. The influence of material property P is analyzed too. For this purpose, the strain energy release rate is plotted against M to F ratio in figure 5 at 3 values of P. One can observe in figure 5 that the strain energy release rate decreases with increasing of P. In conclusion, it should be mentioned also that the analysis described in the present paper can be easily applied for beam configurations with more than 3 longitudinal circular cylindrical cracks. Thank you for your attention.
Thank you very much, Professor Rizov.
You're welcome.
We have the same name, Victor. Okay. Any question from the audience? No one, just a very short answer. Which is the physical meaning of the strain energy and the parameter governing the strain energy?
The physical meaning, in my view, is the strain energy. This is the strain energy that is released when the crack advances. And this parameter, the strain energy release rate, is very important. This is one of the basic parameters, actually, in the mechanics of cracks, of crack advance. Also, when we calculate the path of the crack, one of the ways to determine the path of the crack is to calculate the strain energy release rate and to apply some criteria for orientation of the cracks.
Okay. Thank you very much.
You are welcome.
So it's almost late. We will move to the next presentation. Next presentation is a project overview, practices, objectives, organization, initial findings. Present, Mr. Marcos Sanchez, Sergio Cicero, Arroyo. Please.
I think there is another one, no? Estimation of fracture loads in 3D printed.
Yeah.
Hi, Sergio. I am Sergio Arrieta from University of Cantabria.
Okay. I'm sorry, it's a problem for my glasses.
No
Estimation
problem.
of fracture loads in 3D printed PLE notched specimen using the ASED criteria.
Okay. Can you see my screen now?
Yes, yes, it's okay.
Okay. Well, thank you for the presentation. I'm Sergio Arrieta from the University of Cantabria, and I'm going to present our work entitled Estimation of Fracture Loads in 3D printed plant notch specimen using average strain energy density criterion. Well, this is the structure of the presentation. At the beginning, I'm going to do an introduction. Later, I'm going to explain the methodology that we used. Later, I'm going to speak about the material that we are using and showing the result, and finally some conclusions. Well, as you know, notches produce a stress concentration which leads to the brittle fracture. In this case, we are using the average strain energy density as value criterion. In this research, we applied this methodology to estimate the fracture loads of 3D printed polyacid lattice plates containing U notches. Well, this is the methodology that we are using, is the average strain energy density, and following this criterion, the values of blue occurs in the average value of elastic strain energy. If the values occurs if the average value of elastic strain energy within a certain area is equal to a critical value. The control volume around the notch tip is characterized by the critical radius following these equations. Well, the average strain energy in the control volume is defined by the following equation. It depends on the maximum elastic stress at notch tip, the Young modulus, and two parameters which depends of the notch geometry and the Poisson ratio. Applying IC criterion to the fracture behavior on the 3D printed plates, we estimate which is the critical value from tensile properties. Combining both equations, we obtain the maximum elastic stress at notch tip. Later, we use a Kager Parry equation to estimate the external loads which causes the maximum stress at a notch tip. And finally, we estimate the stress intensity factor for calculating the critical loading. This equation is the one that it should be used for a single edge notch specimen. From a previous work, we have the characterization of the material. And we already know all the mechanical properties for this plant material. These are the specimens that we are now using to estimate the critical loads. They are 3D printed plat with the orientation of 45 degrees. We have performed 27 fracture tests with 2 different notch radius and 3 different thickness, and 2 different radius between the notch length and the width of the specimen. Well, this is a picture of the setup, and some of the displacement versus the load versus displacement curve that we have found in different specimens. The first estimation using the acid criterion give us some really low prediction for loading. So we applied this calibration. As I said, it was validated for linear elastic behavior, and plat is a non-linear material. We made this calibration using the same specimen that we had from this previous work. With these 2 calibration curves, we obtained the asset parameters. A new average strain energy in the control volume and a new critical radius at the notch tip. Applying this new value, we improve the prediction of the loads. So in this case, we increase our 50% of the improving 50% of the predictions. And now to conclude, well, we have used the asset criterion to 3D printed plot using with U-notch and different combination of notch length and width. Using directly the asset criterion, we found excessively conservative critical loads, but applying this calibration, we improved the load prediction, and although they are still conservative, but we are now in reasonable safety margin that is between 1.3 and 2. So thank you for your attention, and if you have any questions.
Thank you, Sergio. Any questions? No one? Just a question, because we have a few minutes. Your approach, this approach can be used also for components made on traditional, not additively manufactured components, or there are some differences between the traditional models?
No, this criterion, you mean this criterion can be used for another composites, or
just for
there is no problem.
But this one, okay.
Okay.
Any questions? No? Thank you, Sergio.
Thank you.
And let's move now to the project overview. Fractuses from Marco Sanchez, Sergio Cicero, and other colleagues present.
Yeah.
Marco, okay. Sergio, can you? Okay.
Yeah.
Thank you. You can.
Okay. Can you see my screen?
Yes.
Okay, thank you. Okay. Hello, everyone. My name is Marco Sanchez. I'm going to present this work entitled Practices Project Overview, Objectives, Organization, and Initial Fundings. Work that has been developed together with my colleagues. Here you have the structure that I'm going to follow in this presentation: a motivation, a brief introduction, what is a mini-sheet specimen, a description of the Fractisus project, a couple of examples from our laboratory, and the main conclusions. As you all know, we are facing right now in Europe an energy crisis. In this sense, the long-term operation of the nuclear power plants seems to be an attractive option, since it's the least expensive energy to be produced. Besides, together with the renewable energies, may help to achieve the energy transition goal proposed by the European Union, which consists of the decarbonization of the energy system by 2050. In this sense, to achieve the long-term operation of the nuclear power plants, it's important to ensure that to guarantee the structural integrity of the reactor pressure vessel. This colossal component plays a key role for several reasons. It's the primary barrier against the release of irradiation into the environment. It cannot be replaced. It suffers from hardening and toughness degradation because of the thermal aging and the radiation exposure, and its failure is it cannot be fair by design or in normal or accidental scenarios. So in this sense, the nuclear power plants have a surveillance program which consists on removing time to time some specimen from the surveillance capsule to be tested. Depending on the specimen you use, you can use different approaches. The first one is based on the Sharpie specimen, which is the most used in current nuclear power plants for historical reasons. The second one is based on fracture mechanics, that is a well-known master curve approach. In both cases, the irradiation is quantified as the shift between the irradiated curve and the unirradiated one. In any case, the problematic here is the lack of material into the surveillance capsule in order to extend the surveillance program that support the long-term operation of the nuclear power plants. So a new proposal was introduced by utilizing a mini-seed specimen that is a compact tension specimen of 4 millimeters of thickness, small enough to machine until 8 specimens from a one broken Sharpie. This idea was, for example, proven by Miura in 2010, who obtained a reference temperature with mini-seed specimen that was in good agreement with those obtained by conventional specimens. Additionally, this mini-seed specimen brings a series of advantages. For example, you can reuse a broken specimen to machine these small ones. You reduce the volume of irradiated material, which is very interesting for safety reasons. You can increase the database by direct measure of fracture toughness, and in case of material homogeneity, you can characterize the local material properties. Encouraged by all these results, all these advantages, a new project called Fractisus began in 2020, thanks to the Euratom funding, and will last for 4 years. The project has been structured in 7 work packages, of which we, the University of Cantabria, are leaders of the work package 6, dissemination, training and education, and data management. In this project, 22 collaborators are participating. The project objectives are the following: to demonstrate the reliability of using mini-seed specimen to measure the fracture toughness of RPV materials, the applicability of mini-seed specimens in combination with master curve approach to characterize the ductile to brittle transition zone, and establish the foundations of mini-seed specimens for its inclusion in future codes and standards. Therefore, by following the technology readiness levels proposed by the European Commission and assume that right now we are in the level 5, the project pretends to achieve the level 7, which means that the mini-seed specimens will be usable in nuclear power plants. So, in the first half of the project, the first important task we have performed is the material selection. Here you have a table above with the different material we are using in the project. All they of great relevance for the nuclear industry. They have different chemical composition, different material properties, and they cover a reasonable wide range of reference temperature. A second important task we are performing are the round-robin tests, which consist on one material to be tested by several participants. In the case of the unirradiated material, we are carrying on 6 different round-robins on which are involved 3 to 5 participants. And in the case of the irradiated material, we have just one round-robin, but with 7 participants. Here you have a couple of examples from the round-robins from our laboratory in the University of Cantabria. The first one is the AMP5 material, and the second one is the A533B material. Applying the master curve approach to our fracture results, we have obtained a reference temperature of minus 26.1 degrees for the AMP5 to 7.2 degrees for the A533B materials. So we compare these results from those obtained by conventional specimens. We have a slightly difference of minus 11.9 degrees in the case of the AMP5 material, 0.8 degrees for the A533B material, which in my opinion are quite good results. Additionally, we have performed a fractography analysis of these materials because it's very important to verify if the main assumptions of the master curve approach are fulfilled with these mini-seed specimens. As you can see at the images, at the beginning of the crack, you have a small ductile area which microvoids are present. Then the rest of the surface is the main micromechanism is the cleavage fracture. Also, you can notice at the edges of the specimen some slant fracture, which is due mainly for the constraint effect. And we have localized a single initiation point in each specimen, or at least a main initiation area. So it's that they are concentrated at the center of the specimen where the triaxiality is maximum. With all this, we have demonstrated that with mini-seed specimens fulfill the weakest link theory, because the main micromechanism is the cleavage fracture and is triggering by a single initiation point. Summing up, I would like to highlight the following points. The mini-CT specimens provide a wide range of possibilities and advantages. However, Fractesius must overcome some uncertainties for the acceptance of mini-CT specimens by nuclear authorities. The initial phase was focused on material selection, crucial for the project progress. The preliminary results from the unirradiated round-robin tests have been obtained, and the irradiated round-robin is ongoing. With this, I conclude my presentation. If you have any question.
Thank you, Marcos. Any question from the audience? No one. So have you checked if is there any differences in terms of results using a conventional CT spaceman instead the mini CT spaceman? In the other, which is the influence of the scale factor?
I mean, for example, for our results, the difference, I think we obtain pretty good results in comparison with the large ones, but it maybe depend of the material. When we have all the results that I saw in the text matrix, we will prepare a more deeply analysis. But for now, the results are pretty consistent.
Thank you. So, no other question. Thank you, Marcos. And we move to the next presentation. The title is Numerical Evaluation of Adhesive Effect on the Peel Strength of Aluminium T-Joints. The presenter is Professor Campillo.
Hello, good afternoon to everyone.
Good afternoon.
Hello. So the title of this work is Numerical Evaluation of the Adhesive Effect on the Peel Strength of Aluminium T-Joints. This work is the result of a master's thesis of a student of mine, João Lopes. The layout of this presentation begins with the goals of this work, then a short introduction to the topic of adhesively bonded joints and numerical modeling, experimental validation of the numerical technique, and then a numerical study on the T-joints considering the geometries, materials, and boundary conditions, the cohesive zone modeling technique for the cohesion assessment, and the results of the numerical analysis. I will conclude with the conclusions and future work proposals. The main goal of this work is to carry out a numerical study of T-adhesively bonded joints between aluminum adherents, considering 4 geometric variables and 3 different adhesives with different characteristics. We want to analyze the stress distributions, damage variable, strength, and the dissipated energy at failure of the joints, and we want to propose the ideal adhesive for applications where the T-joints are mainly under peel loadings. A short introduction to the topic of adhesively bonded joints. The reinforcement joints, as the ones that we see in this slide, they allow for a reduction in peel stresses. They are ideal to bond adherents with different thicknesses, and they add to the structural stiffness under bending. T-joints in particular, they have a significant bonded area, and we must take attention that we need to minimize peak peel stresses to prevent premature failures. The adhesive joints in particular have some applications, for example, in the automotive and aeronautical industries, and they are in constant development. They are also widely used in the scope of composite material bonding, although this is not the scope of this work, and they are structural joints. Experimental validation of the CZM technique was initially carried out by comparing the experimental and numerical results of T-joints bonded with different adhesives. In this validation study, the main parameter that was varied was the T-adherent thicknesses, the thickness of the part which supports the load. And here we can see the results for the case of a brittle adhesive, which is the AV138, which is also studied in the numerical part of this work. And we can see that the numerical models with the proper pre-processing conditions, which replicate the experimental tests, were able to simulate accurately the behavior of the joints. So with this in mind, we are now going to perform a numerical study considering four different parameters, namely the base thickness with values between 1 and 4 millimeters, the thickness of the T component with values between 0.5 and 2.5 millimeters, overlap lengths between 10 and 40 millimeters, and radius of the T component between 3 and 12 millimeters. On the other hand, the thickness of the adhesive was kept constant at 0.2 millimeters. In this slide, you can see the materials used in this work, a medium strength aluminum alloy, 6082, which was characterized for insertion of the respective properties in the numerical models, and three adhesives were considered, ranging from brittle, the AV138, which is a strong but brittle adhesive. The 2015 is also an epoxy adhesive, but with a tensile strain of 5% at failure, and the Sika Force is a polyurethane adhesive with a smaller strength, but with a ductile behavior. The pre-processing conditions were defined to replicate the experimental analysis, namely the boundary conditions, the geometry of the materials. The mesh was created to enable that it is not dependent on the mesh, the results, and a triangular law cohesive zone modeling was considered to replicate or to simulate the damage in the adhesive layer. It may be a simplification for the case of ductile adhesives, but it is ready in the most commercial software. We have a smaller amount of parameters to define, and it provides sufficiently accurate results in most conditions. A stress analysis was initially carried out for the joints, considering the four geometric parameters, and beginning with the peel stresses, and here we only consider the RLD 2015 as an example. You can see, for example, that as we increase the thickness of the base adherent, we have a reduction of the peak peel stresses at the edge of the adhesive because the joint becomes stiffer. On the other hand, if we increase the thickness of the T part, we have an increase also of the peel stresses of the joint because of the concentration of stresses at this same region that occurs due to the higher stiffness. On the other hand, if we increase the overlap length, we have a corresponding increase on the peak stresses, and this is what occurs, for example, in single lap joints because of the higher effects of deformations, lateral deformations. And finally, if we change the radius of the T component, we don't have a significant modification of the peak stresses at the edge of the adhesive, although there are some changes at the region of the radius, but this does not affect the results. The damage variable of the cohesive elements was also addressed, and we can see that there is a significant difference for all of the parameters. For example, for the adherent thickness, for the T thickness, inclusively for one of the conditions, for the overlap length, we have failure at two distinct regions, but only damage at the middle region. It's what happens in this case for an overlap length of 40 millimeters, and also some variation of the damage by changing the radius of the T component. Here we can see the maximum loads, once again for the four variables. Between the three adhesives, the Sika Force 7752 always gave the best results because although it is less strong, it is ductile and it works better under these conditions in which we have stresses concentrated at a very small region. Between the different parameters, we can see that the base adherent has an effect on the strength of the joints, except for over 2 millimeters for the 7752 adhesive. The thickness of the T component also increases the strength of the joint, except for the very brittle adhesive, because this adhesive cannot withstand the high stress concentrations that increase with the thickness of the T. The overlap length also tends to increase the strength of the joints, except for the brittle adhesive, and this is normal because we are increasing the bonded area. And finally, the T radius does not affect significantly the two Araldite adhesives, but it increases the strength of the Sika Force adhesive because it increases load transfer at the region of the radius. Finally, the energy prediction, which is the area beneath the load displacement curves, it is also a measure of performance of the joints. It somehow follows the maximum load of the joints, but here we have to take into consideration that in the joint geometries in which we have plasticization of the adherent, this affects or it increases the energy dissipated at failure. So here the main influences are for the Sika Force 772 adhesive, for the adherent thickness and T thickness, and in the case of the overlap length, we see an effect for the 2015 and 7752, while the T radius only affects the 7752 adhesive. And this concludes the presentation. Here I have a summary of all the conclusions divided by the effect, but here the main important is that we could see clearly which is the best adhesive for this application, which is the polyurethane adhesive, and we could also see the effect of each one of the parameters after validating CCM technique for this particular application. So thank you very much for listening to me. I finished my presentation. Thank you.
Thank you, Professor Campillo. Any questions? No one? Just a curiosity. In your model, how do you take into account the influence of the surface roughness, for example, of the aluminium into joint?
Okay, thank you for the question, Vittorio. Well, in this model, we consider that the adhesive is perfectly bonded to the adherents. So we have only a single component, which we divide into partitions, and then we give, for example, one partition for the adhesive and one partition for the aluminium. And so it is assumed that the bonding is perfect. In the experiments, we just have to assure that we don't have failure at the interface. Which is with the aluminium, the surface preparation is simple. For example, if we perform a sandblasting with specific conditions and then we degrease, for these adhesives, we assure that we have failure in the adhesive.
Thank you very much.
Thank you.
Other questions? No one? So let's move to the next presentation. The title is Effect of Adhesive Type on Tensile Behavior of Tubular Scarf Adhesive Joints. I think the presenter is Professor Moreira, is here.
Yeah, hello, good afternoon.
Hello.
Let me share my screen. So,
perfect.
Sorry.
Yes.
Sorry, but is it scrolling because I cannot see? Oh, okay. So hello, good afternoon. My name is Raul Moreira, and it's a pleasure to be participating in this conference. And I'll present a working title, Effect of Adhesive Type on the Tensile Behavior of Tubular Scarf Adhesive Joints. I'll make this presentation in my behalf, in behalf of our student, José Silva, Professor Campillo, and Professor Isidro Sanchez-Ars. The presentation is divided in the following topics. First, it will be stated the objectives, a small introduction to adhesive joints with characterization of these joints and the strength prediction also used in this kind of joints. After that, the development, it will be presented the methodology, an experimental validation, and then numerical work with, in what we study different parameters, and at the end, the conclusions. The main objectives of this work is the assessment of the cohesive zone model suitability in the prediction of the tensile behavior of scarf tubular joints, as well as understanding the influence of modifying the scarf angle and the type of adhesive. It is also performed experimental data validation for overlap tubular joints, numerical CCM analysis in abacus of tubular joints with different scarf angles and different adhesive types, will be performed the study of the peel and shear stresses in the adhesive layer, and at the end it will be performed the strength analysis of the scarf tubular joints or the P delta curves. Here is a small state-of-the-art review for the adhesive joints. The main advantages are larger area of stress distribution, excellent fatigue resistance, possibility of joining dissimilar materials, and a good strength-to-weight ratio. And the main disadvantages of adhesive joints is that they require surface preparation. They have limited working temperatures, the need of curing process, and low resistance to peel loads. Now a little state-of-the-art review for the strength prediction of adhesive joints. Firstly, it will be presented the analytical models. They are based on differential equations that characterize the state of the stress and the deformation of adhesive bonds. They disregard the variation of the stresses along the joint, use simplifications and assumptions to determine the solution, difficult to account for non-linearities of the system, allows the assessment of the adhesive thickness, joint width, and length variations. It's a straightforward application in parametric studies, and the pioneer formulations were made by Wilkerson and Golan and Reisner. Now, in terms of the numerical models, they are based in continuum mechanics, fracture mechanics, damage mechanics, extended finite element method, and the cohesive zone models. The cohesive zone models enables the analysis of crack initiation and propagation, local and global approximation in the modeling damage. The main limitation is the need to insert cohesive elements in the damage path, and the existence CZMs. They have the shape of an exponential law, linear parabolical, polynomial, trapezoidal, and triangular shape. Now passing to the development, the methodology. Here is presented the main geometries for the tubular adhesive joint. In this case, it will be performed the experimental validation, and afterwards numerical work will be performed in scarf tubular adhesive joints. Here is also presented the main fracture and mechanic properties of the adhesives. The Raldit AV138, which is considered a brittle adhesive. The Raldit 2015, which is considered moderate ductile, and Sika 47752, which is ductile adhesive. Now, in terms of the numerical analysis conditions, the simulations were performed in the Abacus software. They have already built in a cohesive zone model that predicts the strength of adhesive joints. The finite element method analysis were based in the fact that the adherents were modeled with axisymmetric deformable elements, and the adhesive layer was modeled with axisymmetric cohesive elements. Here is the example of the two specimens, the tubular adhesive joint and the scarf tubular adhesive joints. And here is the detail of the adhesive layer. In terms of the boundary conditions, both of the specimens were clamped at one side, and then it was applied an horizontal displacement at the other side. Now passing to the experimental validation, this was performed only for the tubular adhesive joints. Here is presented the low displacement curves for the overlap length of 20 millimeters and 40 millimeters, and this is the case for the Raldit AV138. In gray color is the experimental results, and orange color are the numerical ones. The objective was the validation of the numerical technique in conjunction with the engineering properties, experimental and numerical low displacement curves comparison, and as main conclusion is that the numerical results faithfully reproduced experimental ones. Now it's presenting the results in terms of the maximum strength as function of the overlap length. And here is presented both the experimental and the numerical results for the three adhesives. The adhesive Raldit AV138 and Raldit 2015 presents the smallest relative differences. The Sika 47752 numerical maximum strength values are lower when compared to the experimental ones. The CZM triangular law underestimates the Sika 47752 adhesive, and the obtained numerical results are considered valid. Now passing to a numerical work of the scarf tubular adhesive joints, and here is going to be presented the stress extraction procedure. Here is an example of the mesh used, and the change of the cohesive elements to solid homogeneous elements, a mesh refinement through the adhesive layer thickness, path creation and stress data extraction from Abacus, and then after that, transformation of the stress values in the local system into the correct referential or the global system. Now passing to the results of the peel stress analysis. Here is presented the peel stress analysis for the Araldite AV138, Araldite 2015, and SICA 47752. It is presented the peel stress as normalized by the shear average stress in function of the overlap length. The increase of the peak stresses with the increase of the scarf angle. The stress magnitude along the overlap length tend to be higher with the increase of the scarf angle. As the scarf angle increases, the values of the peel stresses tend to converge with the average shear stress. Due to the transverse deformation of the joint, the peak stress concentrations are located near the bond edges. In terms of the shear stresses distribution, the same display here. Araldite AV138, Araldite 2015, SICA 47752. The scarf tubular joints are characterized by a nearly uniform shear stress distribution along the overlap. There are reduced stress peaks at the bond edges, especially for lower scarf angles. The Araldite AV138 presents the most relevant stress peaks due to its brittleness, and generally there is a slight increase of the shear stress peak for a scarf angle of 3.43 degrees. Now passing on to the strength prediction, the load displacement curves. Also here for the three adhesives, and it is shown for the 5 scarf angles analyzed. For all the adhesives, the maximum strength increases with the decrease of scarf angle. This fact is essentially due to the increase in resistance sectional area of the joints resulting from the decrease of the angle. And the adherent plasticization was found for the scarf joint with a scarf angle of 3.43 degree and bounded with the adhesives AV138 and 2015. Here is the display the maximum strength results in function of the scarf angle. And for all the adhesives, the maximum strength increases with the decrease of the scarf angle. The scarf tubular joints with an angle of 3.43 degrees and bonded with AV138 and 2015 adhesives are the ones that present the highest maximum strength, which is limited by the adherence. And the SICA 47752 reveals the highest percentual increase of the strength. Finally, passing to the main conclusions of this work, the peel stress distribution present peaks at the bond edges, which tend to increase with the scarf angle decrease. The scarf tubular joints practically guarantee an uniform shear stress distribution along the overlap length. The scarf tubular joints are not sensitive to the adhesive stiffness and scarf angle variation regarding the shear stress distribution. The strength of the adhesive joint is highly influenced by the values of the scarf angle, and the strength of the scarf tubular joint depends mainly on the scarf angle and on the mechanical properties of the adhesive. Thank you very much for your attention. If you have any questions, please feel free to ask.
Thank you, Raul. Is there any question? No one. Just a curiosity, my curiosity, how the aging of the joints influence the distribution of the stress between the center and the boundary of the joints?
If I understood correctly, we didn't analyze the aging. So in terms of your question, what I can say is, from my experience, is that as the time influences. Sorry?
The curiosity is about the role of the oxygen or the boundary of the joints, for example. We can have a loss of the adhesion.
Yeah. with the exposition to environment or moisture temperature, okay, the adhesive starts to lose its properties, so the strength of the joint also decreases with the time of exposure to this kind of characteristics.
Yeah. Thank you. So
Okay, thank
we
you
have,
very
we
much.
have no time. Thank you, Raul. And we move to the next presentation. The title is Light Output Dependence of Cerium Brom 3 Hydroscopic Scintillator upon Temperature. The presenter is Christos Mikhail.
Good afternoon. The presenter is Dionysios Linardatos.
Thank you. Please.
Thank you. Just give me a minute to enable sharing because I use a tablet. Please give me a minute. Welcome. My name is Dionysios Linardatos, and I'm going to present a study of the Laboratory of Radiation Physics, Materials Technology and Biomedical Imaging of the University of West Attica. In this study, the light output dependence of cerium bromide scintillator is investigated upon temperature variations. In fields ranging from medical imaging to hostile environments, industrial non-destructive testing, oil extraction facilities, etc., radiation converting materials are essential and their performance is of importance. Material selection has to take into consideration the influence of parameters such as radiation flux and temperature on their light output performance. Cerium bromide is a material with enormous light yield and many advantages over conventional scintillators. On the other hand, its weak points are facility and hygroscopicity. Encapsulation is indispensable for its protection from humidity. Calcium fluoride is mechanically and thermally resistant. Its melting point is above 1000 degrees Celsius. Thus, it can be effectively used in the extreme environments. In this study, the temperature performance of cerium bromide was measured up to high temperatures and compared with the previous results of calcium fluoride for possible integration in medical imaging and hostile environments. Here are tabulated the many properties of both materials. Cerium bromide has an enormous light yield of 60,000 photons per mega electron volt, a short decay time of 19 nanoseconds, negligible afterglow, high atomic number, and emission spectrum adequate for coupling with a variety of optical sensors. Both the examined crystal samples have polished surfaces and equal dimensions, cubic with a 10 mm edge. The aluminum enclosure dimensions were accurately measured by X-ray images obtained by non-destructive testing high-resolution CMOS digital sensor. The back surface has an aluminum thickness of 0.7 millimeters, while the exit window is fused silica glass with a thickness of 1.93 millimeters. The crystals were irradiated using a medical type X-ray unit. An additional 2 cm aluminum filter was added. The above setup was used to measure the crystals produced light up to temperatures reaching 155 degrees Celsius. In order to probe the crystal's temperature, it is removed from the enclosure and the thermocouple is attached on its surface using Teflon tape. The tape covers every side except from the exit surface. To increase the crystal's temperature, a barrel heating gun is used. The temperature is monitored with the thermocouple connected to a multimeter. The scintillator's light is obtained using the experimental setup illustrated here. The crystal is placed in the entrance of a light-integrated sphere. A photomultiplier tube collects the produced light from the output of the integrated sphere. The converted signal from the photocathode is transmitted to an electrometer. From the photomultiplier's signal, the absolute efficiency is calculated. Absolute efficiency is the emitted light energy flux divided by the exposure rate. For determining the exposure rate, the integrated sphere is replaced by a calibrated dosimeter and irradiated under the same conditions. In the graph is plotted the luminosity efficiency as a function of the tube's high voltage. Data are included of cerium bromide with and without the aluminum enclosure, as well as the response of calcium fluoride. The attenuation of the emitted light due to the enclosure is obvious. In another report, it was observed a reduction of the average light yield from 60,000 photons per mega electron volt for samples without enclosure to 45,000 photons per mega electron volt for encapsulated ones. Furthermore, calcium fluoride shows higher luminescence efficiency values for X-ray tube voltages up to 70 kV peak. For tube voltages higher than 80 kV peak, the superiority of cerium bromide, both with and without the enclosure, is clear. In the graph is plotted a comparison between the luminescence efficiency of the examined single crystals in the temperature range from 26 up to 155 degrees. Ranges of this kind can be encountered in logging detectors. Thermal quenching causes the luminescence efficiency of both crystals to decrease with increasing temperature. This behavior is in line with other scintillators previously published. The signal decrease for cerium bromide is more evident for temperatures up to 31 degrees. At higher values, the luminescence signal decreases at a slower rate. For temperatures above 79 degrees, the signal changes only slightly, at around 10 efficiency units. The luminescence light signal output of cerium bromide crystal under the influence of different environmental temperatures was investigated. The results for cerium bromide were studied against previously examined calcium fluoride single crystal of equal dimensions. The cerium bromide sample was examined under X-ray irradiation to assess the luminescence efficiency and was measured within temperatures from 26 to 155 degrees. The luminescence output of cerium bromide and calcium fluoride showed 74% and 79% decrease, respectively, from the room temperature up to the upper examined limit of 155 degrees. Data on the thermal luminescence output of the scintillator can be useful upon the integration of the crystal into detector modules in applications where temperature affects the performance of the imaging system.
Thank you very much. Just a minute.
Thank you, Dionysos. Sorry for my pronunciation. Which is the wavelength of the light?
Cerium bromide has an emission wavelength around
Hello?
400 nano. Did you hear me?
I'm sorry. We have
sorry.
with the
Now, did you hear?
Which is the wavelength?
Do you hear me now?
Now it's okay.
Okay.
The line.
Sorry,
Okay.
sorry. So the cerium bromide emits in a wavelength very very adapted for coupling with photomultiplier tubes, and also with silicon detectors such as CMOS or SSLs.
It's a range,
I
suppose.
The spectral the spectrum is very below the response of these detectors. So the matching factor is very high.
Okay. Okay. Thank you. We have no time, and we have to move to next presentation. Thank you. And the next presentation is entitled Numerical Analysis of an Inline Connection for Hollow Section. The presenter is Professor Both. Johan Both.
Hello. The presenter will be Kalim Birdian. Johan Both is my colleague.
Okay, okay. Please.
I apologize because I'm from a desktop and I don't have a webcam, but I managed to put a picture with myself so that you can see me. I'll share my screen.
Yeah. Okay.
Okay. So you can see it. So the paper is called Numerical Analysis of an Inline Connection for Hollow Section. The paper presents the result of an experimental program of an inline connection for rectangular hollow sections, which stand as a reference for a validation of a finite element model. I will start with a short introduction by saying that nowadays the most challenging thing in engineering of the envelopes of the buildings are the shapes of the envelopes that architects requires. So I brought here some examples. Musée de Confluence in Lyon, the architect imagined a cloud, that the building should look like a cloud. At the bottom, we see the World Financial Center in New York. This is a glass curtain hanging on two steel trees. Further on, Novartis campus, we can see glass blocks stacked to each other. And the last one is in Canada, Museum of Human Rights. It represents a bird that closes her wings together. I brought here for the last two pictures in daylight and in night, because not only the envelope, the shape of the envelope is important for the architect, but also the structure, the main structure is also a key factor for them, because the architectural exposed systems nowadays represents the trademarks of the buildings. We can see here at the top the glass funnel inside of the Musée de Confluence in Lyon, with the primary structure, with the steel structure, and at the bottom the steel trees in New York. Another challenge is not only the shape, but bringing this to reality and finding the right type and the right location of the connections of this structure, of these tubes. For example, at Musée de Confluence, we can see here with yellow points where they have been, and here they've been sliced in New York by different lengths. Of course, it has to be considered limitations of transportations, limitations of installations, and the economical factor plays also a key role in designing these connections. And in order to that the architects are satisfied, let's say, and their requests are met, we as engineers, we have to shift from the regular end plate bolted connections on the left side that are visible to the non-visible connections, and shift all the head plates, all the end plates, screws, everything inside of these tubes. And of course, make them disappear, make that the shapes are flowing without any interruptions in the entire building. An experimental stand was set up. Each element assembly consists of RHS tubes, 250 times 150, 8mm thickness profile with a support end plate and the connection end plate welded, as I said, inside of the tubes. Each element assembly had a cut 150 times 110. This is a hand hole, so-called hand hole, so that the M20 bolts can be pre-stressed. A gap of 4mm between the two end plates have been left so that the load, the forces would flow only through the cross section of the tubes and not through the end plates as in a regular connection. The boundary conditions at the supports allowed free rotation of the specimen ends as well as free horizontal translations, we can see here. A digital image correlation system was used that allows to monitor the deformation of the local area, similar to the strain gauges. Moreover, the distance between the virtual strain gauges can be monitored such that the separation between these gauges is recorded. As a result, we can see here that the two specimens that were tested are quite similar in terms of force displacement curves and moment displacement curves. And another key factor in this type of joint is the joint separation in millimeters or fractions, actually, of millimeters that have been investigated with this 3D optical system. Further on, a finite element model was defined to observe the response of the joint and for parametric investigation. The analysis was performed using the software, the well-known Abacus. The material properties were considered from the tensile tests performed on the specimen extracted from the tubes and from the bolts materials. A pin and a roller were defined at the assembly end, while a displacement of 30mm was defined using reference points in the point load positions. Each part was meshed. Of course, the size of the element in the mesh was approximately 5mm, allowing to obtain two rows of elements around the cross section of the tube. And in order to reduce the computation time in the longitudinal direction of the tubes, the mesh was increased. As a result, a short comparison on the left, we can see between the FEM model and the experimental results. We can see that a very good correspondence is obtained for the initial rigidity of the assembly, although the maximum force is
Johan, I'm sorry, you have just a minute.
Yeah.
That's okay. Okay, please.
So the reality from the experiment is quite similar with what we obtained on the FEM model. And further on, we have studied the influence of the access hole, the influence of the preload of the bolt, and the influence of the end plate thickness. As a conclusion, we've seen that aesthetic considerations are imposing structural components to be designed in an uncommon way. That means we have to take care that the joint doesn't open. This is a visual aspect that has to be considered. The study shows a small decrease in the rigidity of the assembly due to the cut of the RHS profiles. A small influence is also shown by the preload level due to the distance between the connection end plates. This distance is set such that the profiles to be in contact for a continuous, as I said, aspect of the joint. And a great influence in both rigidity and capacity is assigned to the thickness of the end plate. The end plate thickness, due to its deformation, leads to major bending imposed to the bolts, thus a smaller capacity of the connection. Thank you.
Thank you, Johan, but we have no time for questions. Please, let's move to the next presentation. The title is Parametric Analysis of Double Lap Composite Adhesive Joints Under Impact Loads. The presenter is João Valente, or Raul Campillo, or Luis Gomez.
It is me, Raul Campillo.
Hi, Raul.
Hello, hello once again. So good afternoon, everyone, again. The title of this work is Parametric Analysis of Double Lap Composite Adhesive Joints Under Impact Loads. The main author of this work is Luis Gomes, which is a master student of mine. The index of this work is divided into the objectives, joint geometry and dimensions, materials, numerical analysis conditions, validation of the cohesive zone modeling technique under impact with experiments, considering the drop test, and then the numerical results regarding stress distributions and the strength prediction as a function of the overlap length, and the assessment of the CZM parameters effect on the outcome of the simulations. I will finalize with the conclusions and suggestions for future work. The main objective of this work is the validation of CZM for impact strength prediction of bonded joints, experimental and numerical study of double lap joints under impact, and evaluation of an important geometrical feature, which is the overlap length between 12.5 and 50 millimeters, and comparison between different cohesive parameters. The adherents and adhesives are also going to be explained in this presentation. Here we can see the geometry of the double lap joints. Here the main parameter to modify is the overlap length between the adherents, while all of the other parameters remain constant. The materials are two adhesives, the Aralite V138, which is a brittle epoxy adhesive, the 7752, which is a ductile polyurethane. In these figures, we can see the properties under impact, which were estimated by extrapolation from properties at high speed, and the adherents are going to be fabricated from a unidirectional carbon epoxy prepreg with the properties presented in this table. Validation with experiments was initially carried out. We considered the drop weight machine, considering a 30 kilogram anvil with a height that would produce an impact energy of 40 joule. Numerically, the analysis conditions involve the CZM elements to model the adhesive, triangular CZM shape, a global mass size up to 0.2 millimeters, which is the thickness of the adhesive layer, and the impact energy of 40 joule was emulated by applying a specified initial velocity to an artificial mass created at the end of the joint. Here we can see the validation of the results with experiments. First, beginning with the AV138 adhesive, we can see that we have a good correspondence between the average experimental values and the numerical ones. The highest error was found for 50 millimeters overlap, but with an error below 5%. And here we can see the results of the validation for the 7752 adhesive, in which the highest error was about 13% for an overlap length of 12.5 millimeters, while the other ones were kept inside the experimental deviation. So we consider that the proposed approach, in which we tune the properties to the velocity applied to the adhesive, is a good and accurate technique for this type of joints. Here we can see shear stress distributions for the joints with the two adhesives. Here we are already talking about the double up joints of the numerical study. We can see that for both cases we have an increase in peak stresses as we increase the overlap length, because we have an increase in shear lag factors. We can also see that there is no symmetry between the two edges of the adhesive. This is because we have a double up joint geometry, and the differential straining effects in both adhesions are not the same as it occurs, for example, in single up joints. And finally, we can see that the normalized peak stresses are much smaller for the compliant adhesive than for the brittle adhesive, since this is a characteristic feature of this type of joints. For the peel stress distributions, the same conditions apply, which means that we have an increase in peak peel stresses at the overlap edges with increase in the overlap length. We have also a reduction of peak stresses by shifting the adhesive from the AV138 to the 7752, and we have a stress distribution in which peel stresses are mostly applied at the edges of the adhesive. Here we can see the P delta curves obtained numerically for both adhesives. We have the characteristic oscillatory behavior up to the maximum load that occurs under impact due to the inertial effects. We can see that the Pmax are higher than for the single up joints, because on one hand we have the double of the adhesive bonded area, and on the other hand we have less peak stresses due to the double up geometry. We also see that increasing the overlap increases the strength of the joints, which is the peak value of the curves, and also that this increase is higher for the 7752, while for the AV138 it seems to have a plateau value above 25 millimeters of overlap. Here we summarize the results obtained from the P delta curves. We can see that the AV138 has higher maximum load than the 7752 adhesive, because it is stronger in terms of bulk strength, but it has a smaller improvement in the Pmax as we increase the overlap length. And this is because this adhesive is brittle and it is more affected by the peak stresses that increase as you increase the overlap length. We can see that by the percentile increases over 12.5 millimeter, in which the value for 7752 is almost a threefold increase in the value of 12.5 millimeters. A CCM parametric analysis was also carried out to assess the effect of different modeling conditions. The first issue to test was to uncouple tensile and shear cohesive loss in the numerical models. And we can see that there is a difference. For example, for the AV138, the difference is up to 10 to 11%, while for the 7752 adhesive, the difference reaches almost 30%. So we can conclude that for more brittle adhesives, there is a lesser effect on uncoupling both modes than when we use ductile adhesives. If we compare the elastic stiffness of both adhesives and making variations between -75 and more than 100% of the initial values, we can see that there is an effect, and that this effect is higher for the brittle adhesive, with variations up to 80% of the initial strength, while for the ductile adhesive, this difference reduces to 15%. Regarding the tensile cohesive strength, by varying this parameter with the same limits, minus 75 to 100%, we have a higher difference for the EV138, up to 20-25%, while for the 7752, these values reaches almost 14%.
Raul, I'm sorry, we have just a minute.
Okay, thank you.
Please.
Okay, thank you. The effect of the shear cohesive strength is similar, but here the difference goes up to 60%. The combined effect of tensile and shear cohesive strength is close to the shear cohesive strength. And on the other hand, the fracture energies in mode 1 and 2 have virtually no influence on the results. And this occurs for the AV138 and also for the 7752. So to conclude, in this work, we managed to validate the CZM technique with tuned properties of the adhesives to predict the strength of the double up composite joints, and we could see the effect of the main variable of geometry, which is the overlap length. So thank you very much for listening to me, and if you have any question, I'm free and happy to answer. Thank you.
Thank you, Raul.
Thank you.
I think we have no time for the question, and let's move to the next presentation. Is temperature dependence of luminescence output of trichloride lanthanum cerium single crystal scintillator. Who is the presenter? Is there any presenter of the temperature dependence of luminescence? Authors are Stavros Seremoglou, Vasilios Neptis, Dionysis. No? Okay, let's move to the next presentation. The title is Fatigue Reliability Analysis of Load-Carrying Cruciform Welded Joints Considering the Misalignment Effect. The presenter is Wei Song.
Yes, I'm here.
Yes, please.
Okay, I shall share my presentation first. Can you see the presentation?
Yes.
Okay. I should open
Perfect.
the.
No,
okay. I should open the. Open the video. Oh.
It's okay. It's okay. Please.
Okay. It's okay. No. Okay, I can start my presentation.
Yes, do. Please do.
Okay. I should delete this. Hello everyone, my name is Feng Wei. I'm come from Xuzhou University of Technology. It's great pleasure to have this opportunity to present this talk today in the conference. This focus of my work will be on the fatigue reliability assessment of load carrying cruciform welded joint with undercut and misalignment. So I'd like to acknowledge the support for the funding of fundamental agency and industry partner. My work including 4 parts. The first one is the motivation, and the second is the fatigue experiments, and the third is about the result, and the fourth is the conclusion of my work. As we all know, some background of the motivation for the work is about the industry development. One of the effective way to enhance the lightweight of structure to increase the strength of steel for this decreasing the thickness of the plane is dealing with conventional material for the marine structures and shipbuilding structures. So on for this high strength steel welded, there's we cannot avoid the some defects in this welded joint, such as the misalignment and undercuts defects, and also the welding deformation. So the misalignment.
Yes. Hello.
Misalignment. Can you hear?
Hello, can you hear me?
Yes, yes.
I'm sorry, I'm Stavros Teremoglu. Sorry for the interruption. I wasn't able to speak previously. I'm really sorry.
No problem. Please wait.
Okay,
Yeah.
thanks. Sorry.
I continue my.
Yes, please.
Okay. So the welding deformation, including the angel or axial misalignment, so it affects the fatigue strength and the fatigue life of welded joint. So if we want to solve this problem, we should to the quality control or using some the anti-destruction. But for this problem, for this welded joint, the fatigue reliability should be access. So this study aims and the investigating the undercut and the misalignment effect on fatigue life of the crisp welded joint. In this work, the stress distribution and the third K for RCWG considering the undercut and the misalignment. So finally we can get the reliability index for the RCWG considering this defects effect. Firstly, we did some fatigue test considering the misalignment effect. Like this, we can find that this is this angle misalignment, and this exists the axial misalignment. So we did the fatigue test using the MTS machine, and then we did some fatigue crack growth test about the high strength steel in China, and including the best material and the undermatched weldment and even matched weldment, including the HAZ materials. So we did we conducted this test under different stress ratios. We did the stress ratio 0.1 and 0.4 and 0.7. So we get this result in this figure. Finally, we using the NASGRO equation to fit in these curves and get some distribution of probability parameters for the estimation of the reliability index. In our study, we did the investigation using based on the fracture mechanism method. So this is the procedure of my work, including the firstly we can get the stress distribution, including the defects, and then we use the NASGRO model to get the delta K, and using the weight function theory to estimate the stress, the delta K. Then this is the FE simulation about the result. We can see this result FCG data owns a good agreement with the experimental data. So next we calculate the the notch stress, including the undercut, such as the dips, different dips and the wells, to get the stress distribution. And then we consider the axial misalignment.
I'm sorry, wait, the time is almost finished. Just a minute.
Okay. Then we get the stress distribution near the defects. And then we using the probability statistic model to estimate the fatigue strength using different distribution equations. And then we get the fatigue strength under different considering different material properties and the defects. So we get the fatigue life distribution under this defects. Then we can get the probability statistical relationship with fatigue life and the fatigue and the failure probability. So
wait, you have to move to the conclusion, please.
Yes, this is the next page. Okay, we can see the reliability index about the fatigue strength. So this is my conclusion. So I have no time to show this. Thank you.
I'm sorry, but the time is very short because we have a lot of presentation. We have no time for the questions. So I want to call another one, the presenter of temperature dependence of the luminescence output of chloride, lanthanum, cerium single crystal scintillator is here, the presenter.
Yes, can you hear me? Can you hear me now?
Yes, please do.
Okay. I'm really sorry for the inconvenience. Let me start.
Yes, wait, please leave the.
Yeah, sorry, I wait for a moment.
Perfect, okay. Please.
Let me share my screen.
Yes.
Can you see it?
Okay. Okay, it's right.
Okay. Hello, everyone. Thank you very much for attending my presentation. My name is Stavros Tseremoglu, and I'm a PhD candidate at the Department of Biomedical Engineering in the University of West Attica in Athens, Greece. Today, I will present you a study on temperature dependence of the luminescence output of lanthanum chloride single crystal scintillator activated with cerium. The experimental part of the study was conducted in the laboratory of radiation physics, materials technology, and biomedical imaging of the University of West Attica. Allow me to start with a brief introduction to scintillators. Crystal scintillators are used in various applications in order to convert radiation to light, and they have been widely employed in several technological fields, from industry up to nuclear physics. Namely, some of these applications include medical imaging, nuclear reactor monitoring, oil and gas industry, as well as space and marine exploration. In harsh environmental applications, where extreme conditions of pressure, temperatures, or radiation fluxes occur, the performance of a scintillator is strongly affected by these parameters. The aim of the study is to investigate the absolute luminescence efficiency dependence of a lanthanum chloride crystal scintillator over a wide temperature range. Lanthanum chloride crystal activated with cerium was selected due to its distinct advantages, such as high light output and fast decay time, providing excellent energy resolution performance. The reported light yield ranges from 40,000 to 49,000 photons per mega electron volt, depending on the size of the crystal and the cerium concentration. In addition, its response is very linear, meaning that its light yield is energy independent. The high light yield and the very good linearity of the crystal response are the reason for its excellent energy resolution. Moreover, the crystal has a fast response time from 20 to 28 nanoseconds, and the high melting point at 1135 degrees Celsius, providing robustness at high temperatures. As I mentioned previously, the suitability of lanthanum chloride crystal scintillator was evaluated by the absolute luminescence efficiency dependence of the crystal over a wide temperature range. Absolute efficiency is defined as the ratio of the energy flux of the light photons emitted by a stimulated crystal over the incident exposure rate, and its unit in SI is known as efficiency unit EU. For the experimental part, a single cubic shape crystal was irradiated using an X-ray tube. The measurements were performed over the temperature range of 29 to 162 degrees Celsius using a heated gun to heat the crystal, and the temperature monitoring was performed with an infrared digital thermometer. The examined temperatures kept at this range to avoid the excessive heating that could result in possible crystal cracking. In this slide, you can see the experimental setup for the calculation of absolute efficiency. For the energy flux measurement, a light integration sphere, which is used to improve the uniformity of the beam, was coupled to a photomultiplier tube. The tube was connected to an electrometer, and the readings of the electrometer give us the light energy flux. The exposure rate was measured with a Piraha dosimeter. This graph shows the variation of absolute efficiency measured values of lanthanum chloride crystal, with the temperature ranging from 29 to 162 degrees Celsius. With increasing temperature, the luminescence efficiency in the range 29 to 84 degrees Celsius decreases almost exponentially, with the absolute efficiency values ranging from 33.14 to 70.96 EU. This decrease of luminescence efficiency, which is well known as thermal quenching, is characterized by loss of light emission with increasing temperature due to the non-radiative relaxation processes, which are enhanced with an increase in temperature. From 84 to 162 degrees Celsius, the emitted signal is quite stable, as the luminescence efficiency is little affected by the increase of the temperature, with the absolute efficiency values remaining almost constant. This temperature stability of lanthanum chloride crystal is very helpful for practical applications at high temperatures, such as oil and gas industry. To sum up, in the current study, the absolute luminescence efficiency of lanthanum chloride single crystal scintillator activated Gaussium was investigated in a wide range of temperatures. From the measured absolute efficiency values, the efficiency of the crystal showed a 47% decrease from 29 degrees Celsius temperature to the maximum examined. Considering this fact, as well as the temperature stability of the absolute efficiency values at temperatures above 84 degrees Celsius, we may conclude that lanthanum chloride single crystal scintillator could be considered as a suitable choice for applications at harsh environments where extreme variations of the temperatures occur. Thank you very much for your time and attention.
Thank you very much, Stavros. There is a time for a question.
Okay.
No one? So, just one short answer.
Okay.
How is defined the efficiency?
Sorry, the efficiency?
Yeah.
It's right here. As the ratio of the energy flux of the light photons to the incident exposure rate.
Okay. Okay. Thank you very much.
I'm again really sorry for the inconvenience.
Okay. No other questions. So thank you, Stavros.
Thank you very much.
Next presentation, the title is Effects of the Geometrical Imperfections on the Ultimate Strain Performances, a case study on the designed steel stiffened panel. Who is the presenter?
Okay, can you hear my voice?
Hi. Please.
Okay.
The presenter is Muhammad. Okay.
Okay.
Please do.
Can I start now?
Yes, do.
Okay. Good afternoon, everyone. My name is Muhammad Imaduddin Hanif. In this occasion, I will tell you about my research, the effects of the geometrical imperfections on the ultimate strength performance, a case study on the design steel stiffened panel. So in the first section, we move to introduction. As we all know, activity of export and import across the globe is inseparable from commodities trading across the globe. In this study, we will more concern about bulk carrier. Bulk carrier itself has three advantages. The first one is large capacity. The second one is have affordable cost, and the last one is withstand various loadings and conditions. But in another case, there is a whole girder accident that occurred in a bulk carrier. According to published data by Enwigwe et al. In 2022, until the end of July 2022, there had been a total of 34 accident cases on bulk carrier. For that reason, we have to concern more about hull girder ultimate strength, or HGUS, that the ship can be answer safe if the value of HGUS exceeds the total bending moment value at the specified margin. The IGF27 in 2022 uses method to determine the relationship between moment and curvature in which progressive failure and post-buckling of stiffened panels by dividing and categorizing the ship hull into elements, including stiffened plate elements, hard corner, and plate elements that adapted from Smith in 1977. But there is a factor that we have to more concern. That factor is initial imperfection geometric, because the initial imperfection geometric can affect the value of ultimate strength and the collapse behavior of a hull girder. On the last research, the geometric imperfection is assumed as a single value based on the plate slenderness, as has been done by Khan and Zhang in 2011 and followed by Anifantis in 2020. So the purpose of this paper is to vary the degree of initial geometric imperfection into standard imperfection and the severe imperfection. So this is the picture of the hull girder cross section of the ISSC 2000 bulk carrier. The load shortening formulation of stiffened panels based on IGF27 were derived based on equation 1 until equation 3. So before performing calculation using finite element method, it is necessary to simplify the model of the stiffened panels that make up the hull structure. The configuration of the model that we use is half plus half by half plus half span model, and the properties is here. So the scatter data is referred to determining the initial imperfection value in the stiffened panel geometry. So for this data here is referred to Fujikubo et al. In 2005, and the line here and here is the function of the slenderness and the thickness of the plate. The formation of initial imperfection on the design structure. The used formula to calculate the initial imperfection geometric on the stiffened panel is shown in a table here. So let's move to the boundary condition and meshing. So for the boundary condition and meshing is you can see here. So let's move to result and discussion. So here there are three graphs. The first one is a large shortening curve of short heavy model based on IXCSR. The second one is a large shortening curve of short medium model based on IXCSR. And the last one is large shortening curve of short light model based on IXCSR. So based on the rules that from IXCSR, as we can see here for the graph 1 until the last one, the minimum value here is torsional buckling. So from the rules that state in IXCSR, the value that we will get as a parameter of ultimate strength is from the last one. So in this case, we will use the torsional buckling value. So let's move to the next graph. Here we can see the loss shortening curve of a short heavy model based on a finite element method. In this graph, as we can see, for the initial imperfection geometric of 2.5% and 25%, will have a will be greater the ultimate strength value than the ultimate strength value of a torsional buckling mode based on IXCSR. On the other hand, the initial imperfection geometric of 100% and 300% will be lower than the ultimate strength value based on IXCSR. So let's move to the first table. The first table is the value of ultimate strength over yield strength, and the ratio of ultimate strength based on finite element method over ultimate strength based on IXCSR. So on the yellow box, as we can see, the larger initial imperfection will have the lower the ratio of ultimate strength over yield strength. So the initial imperfection will affect the value of ultimate strength. And another hand, in the blue box and purple box, as we can see, imperfection value of 2.5% and 25% will be greater than the ultimate strength value based on IXCSR. As we can see, the ratio of ultimate strength value based on finite element method over IXCSR with the initial imperfection of 2.5% and 25% almost above 1. On the other hand, for initial imperfection, 100% and 300% is below 1. And the second table is summarized ratio between ultimate strength based on equation and the ultimate strength based on a constant value. As we can see, the way to determine the 300% imperfection value for slenderness plate value of more than 60 influence the ultimate strength value. So the conclusion that for this study are, the first one is all stiffness panel models with initial imperfection geometric variation of 2.5% and 25%. We have an ultimate strength value greater than the ultimate strength value obtained from the IXCSR method. The way to determine the 300% imperfection value for stiffness panel with slenderness plate value of more than 60 influences the ultimate strength value. And the last conclusion that we get is for future studies, it is necessary to carry out an analysis with a wider variety of initial imperfection geometric to be able to determine the pattern of distribution of ultimate strength values. Thank you for your attention. That's all for me.
Thank you very much. There is any question from the colleagues? No one. Just one consideration about the influence of the in the conclusion. Can you show us the last one slide, the conclusion slide? The second point, the way to determine the 300% of imperfection, it's a very high values. Some more words about this.
Okay, I will answer your question, sir. So
yes,
the 300
some more words about this number because it seems to be very high.
Okay. So on the last research by Anifantis is a single base value. The value of imperfection is 100%. So in this study, we study on 300% imperfection because it's refer to the ship condition that have a poor maintenance condition.
Yeah.
So for the 100% is a standard condition.
Yeah, yeah. 3 times higher than the standard condition.
Yeah.
Okay.
Yeah. Okay.
Thank you very much.
Okay.
Thank you,
sir.
Muhammad. And we move to the next presentation. The title is 3-point bending assessment of cold water pipe sandwich material of ocean thermal energy conversion. Who is the presenter?
It's me, Mr.
Oh. Andriel, please.
Yes. Can you see my screen?
Perfectly. Yes.
Okay, let me start. Hello, let me introduce myself. I am Andriel from 11 Maret University. In this presentation, I will explaining about my study entitled 3-point bending assessment of cold water pipe, or CWP, sandwich material for ocean thermal energy conversion, or OTEC. This work has carried out in collaboration with Badan Riset dan Inovasi Nasional Indonesia. We can see in this slide, there is 9 content that I will explain in this presentation. The first one is introduction. OTEC is a power plant that utilizes the temperature difference between sea level and the depth of the sea. This temperature difference is ranging from 5 to 7 degrees Celsius. Cold water pipe, or CWP, is a pipe that hangs on the OTEC platform, which functions to deliver low temperature deep sea water to the OTEC platform, where there will be a heat exchanger processed with the water on the surface. We can see on the red box is the cold water pipe. This box. CWP structure requires strong structure, but also needs to be lightweight. Next is scope of study. In this paper, the author will discuss mass-produced material to facilitate in making cold water pipes. The sandwich material was chosen as a solution for use in cold water pipe due to large strength and weight ratio. The material is chosen is Nomex honeycomb as the core of the sandwich and carbon fiber as the facing. This paper will discuss sandwich structure flexural strength by 3-point bending testing and finite element analysis. Next is sandwich material. Sandwich structure are like multifunction composite structure constructed by embedding a core between 2 facing. In order to obtain good mechanical performance, the sandwich structure typically has stiff facing and lightweight core. We can see in the figure 2, the composition of sandwich material consisting of single core and 2 facing embedding it. Sandwich material is fit to use in CWP because the nature of sandwich material is lightweight, can keep its shape, and have a strong tensile and flexural strength. Next is methodology. There are 3 steps in performing this study. First one is laboratory testing. Second one is numerical simulation. The third one is mass convergence study. Laboratory testing. In laboratory testing, we use ISTM D7264 as standard test method for flexural properties of polymer matrix composite material. In figure 3, we can see the dimension requirement of ISTM D7264. Next is testing result. The testing stopped when maximum point load has been reached. Laboratory testing has shown a crack on the upper facing of the sandwich structure. When maximum point load has reached, core and bottom facing part did not damage at all. The damage on the core and bottom facing will happen exponentially with the progress of testing. Next is laboratory testing result. We can see in the figure 5 the result of laboratory testing graph. Based on laboratory testing, we have obtained maximum elongation of the specimen is 6.88 millimeters, with the maximum point load of specimen is 200.11 Newton. Next is numerical simulation. First is boundary condition. We can see in the figure 6, point A is a load and point B is a jig. In point A, we set boundary condition as a displacement with U2 equals 15 millimeter, and the point B is an caster. The next one is meshing configuration. Meshing on two parts of the sandwich uses different seed size in the facing. In the facing section, it has 6,350 elements with a seed size of 1 millimeter. The core uses a seed size of 2.25 millimeter with a total of 1,630 elements. Material properties setup. The first one is core properties with Nomex aramid honeycomb. These material properties are sourced from paper written by Roy in 2014. The material properties are input on engineering constant on the electric properties menu. Next one is facing properties or the carbon fiber. Material properties are collected from previous existing paper. The properties are collected from papers made by Isbiller in 2012. In the original paper, the properties are unidirectional carbon fiber. In this paper, the author assumes the strength of E1 equals to E2 for bidirectional carbon fiber that used in the study. Modeling of carbon fiber is using lamina with hazing damage. Next is numerical simulation result. The result of numerical simulation is similar to the laboratory testing result. Numerical simulation also shown damage on the upper facing similar to the laboratory testing result. In numerical simulation result, we can see the damage that happened after the specimen reached maximum point load. Damage is expanded on the core section and bottom facing as test continues. Next is mesh convergence study. A mesh convergence study carried out by changing mesh sizing only on the facing part of the model. The core part of the model is fixed with 2.25 millimeter size. A mesh convergence study was conducted to determine appropriate configuration when performing the numerical simulation. We conclude that the best mesh configuration that good to use in the study is 1 millimeter with a total 6,350 elements. This mesh configuration was chosen due to good accuracy and small compute time. Next is benchmarking. Benchmarking is carried by comparing simulation result with 3-point bending laboratory test result. The numerical simulation result, the black line, should not differ by more than 10% compared to laboratory test result, the red line. We can see the maximum point load differed by 2% and the elongation differ by 7.7%. The last is conclusion. The actual test result using a 3-point bending test obtained the maximum strength of sandwich material is 200.11 Newton, with a maximum elongation is 6.88 millimeter. It is known that during the test, the specimen lower facing did not experience failure during the test. Only the top and the core were damaged as the test progressed. Thus, it can be concluded that the carbon aramid Nomex sandwich material is resilient. From the benchmarking result, it's known that the numerical simulation result are at the maximum stress point of 195.909 Newton, or 2% smaller than the actual test result, while the elongation is obtained at 6.35 millimeter, or 7.7% of the actual test result. These results are influenced primarily by material configuration and mesh configuration. That's all from us. We hope this study can be useful in the future study, especially in structural field. Thanks for your attention. For those of you who have questions, please ask me.
Thank you, Andriel. Any question from the audience? Okay, Andriel, can you show us the conclusion, please? Yes. In the first point, you talk about a maximum elongation of 6.88 millimeters in a bending test. But I think this is a deflection. It's not an elongation because it's a bending test.
Oh, I see.
Okay. Please, can you tell us which is the total thickness of the specimen?
The total thickness of a specimen is 4.5 millimeter. I forgot to written in this presentation. I'm sorry, sir.
Thank you very much. So
yes.
I have one question.
Questions from the audience?
Yeah, I have
Please.
one question.
Just a short question, please.
Do you have the form of the material property matrix here?
Excuse me?
The form of the material properties matrix.
I think this is, sir.
The form or the shape?
Yeah. Here are the components, but the form, the matrix.
Okay, the shape of the matrix inside the composite material is hexagonal, it seems to be.
Is that the orientation of the carbon fiber, sir?
No, the form, the shape.
Oh, yes, the core, the shape. This
I
is
think
the.
this is the
yes.
The design.
This is the
Okay.
core part. Is the shape is like honeycomb.
It's okay.
The stresses are sigma equal the material properties matrix D dot epsilon deformations strength or strength. I am asking to show the form of this material properties matrix D. D multiplying by epsilon, the strength. How have you computed these constants E1, E2 with software, or have you the expression of the material?
Yes, yes. In this study, the material properties are sourced from paper written by Roy. So I take the material properties and input it on the numerical simulation, and then I sort of matching it with laboratory testing, and then the graph is the same. It's like that, sir. So it is like a mix and match.
Okay, I'm sorry, but we are late. We have to move to the next presentation. If you want, you can talk on the chat together. Okay. So the next presentation, the title is Nonlinear Assessment of Cold Water Pipe on the Ocean Thermal Energy Conversion Installation under Bending Load. Who is the presenter?
I am, sir.
Please do.
Okay. Good afternoon, ladies and gentlemen. My name is Prayoga Wiraadi from Universitas 11 Maret. We'll present to you about my research about nonlinear assessment of cold water pipe, or CWP, on the Ocean Thermal Energy Conversion, or OTEC, installation under bending load. In this presentation, I will explain the introduction why of this research need to be done, the previous study of related to buckling, the finite element setting used in this research, the result and discussion of this research, and the conclusion. Introduction. The Ocean Thermal Energy Conversion, or OTEC, is a floating platform that functions to convert energy, seawater heat energy, into electricity. Cold water is taken from the sea with depth of 800 to 1000 meter through cold water pipe, or CWP. This long CWP size causes unavoidable bending load due to seawater flow. The extreme diameter per thickness ratio of the CW pipe makes this pipe susceptible to buckling. In this research, numerical validation and mass conversion study was carried out for CWP OTEC research under the next bending load. Objective and scope of the work. This research was conducted to validate the numerical analysis and find the mass convergence. A cylindrical cell is used as a model in this study. The cylinder is given a moment on the one side and the other side is fixed end. The number of mass used in this is varied in order to obtain a convergent mass. Previous study about buckling. The following equation are some of equation that have been made from previous study that have been carried out. The critical moment formula can be seen in equation 1. The moment in the plastic region can be seen in equation 2. And the relationship between moment and pipe curvature can be seen in equation 3. Finite element setting, geometry. For the current study, the model from Yadav and Geramisis was reproduced for future research. In the study, the radius per thickness ratio used was 60, using the model shape imperfection model with an imperfection magnitude W0 per T of 0.1. The diameter of the cylinder is 4,000 millimeter and the length is 2,000 millimeter. Finite element setting material properties. The material used in this model is steel. The steel has a yield strength of 355 MPa, Young's modulus of 210 GPa, and Poisson ratio of 0.3. In this model, Rambert-Osgood plasticity model is used. For Rambert-Osgood model equation for the steel can be seen in equation 4. Boundary condition. In boundary condition, one side of the pipe is fixed. So U1 equal U2 equal U3 equal UR1 equal UR2 equal UR3 is equal to 0. And the other end of the pipe was applied moment. Result and discussion, benchmarking. In this validation, the result of the present study will be compared to the result of Yadav and Geramisis in 2019. The results were obtained using static Ricks method in the Abacus software. The moment is normalized by t square times by t times by sigma y, and the curvature is normalized by t over t square. The similarity is in the elastic spark when the two curves coincide. In addition, the similarity can be seen in the post-buckling where two curves also coincide. However, the place where the critical moment occurs in the reference is earlier than the study conducted. This can be caused by different material input, especially during the transition between elastic and plastic deformation. In this figure, the stress control is when there is no load, so there is no stress occur. When the observation is continued to this figure, it can be seen that the structure has undergone plastic deformation. It can be seen in the maximum stress that has exceeded given yield strength. However, it not yet past critical moment. In the next figure, it can be seen that the structure has passed critical moment, so that at the time the structure has failed. When it's continue, it can be seen in this figure, where the failure area will get bigger. In this case, the stress propagation only occurs on the one side and the one direction. This is because the component of this structure is just one component. Displacement control. For displacement control, it can be seen that the displacement occurs only half of the pipe. The higher the end of the pipe, the greater the displacement that occurs. This can be caused by strain that occurs. From the strain contour, it can show that the strain that occurs only in the middle of the pipe. Mass convergence study. In this study, a convergent mass study is carried out to determine the mass that can use for further research on the OTEC. In this study, a mass convergence study was carried using the step buckle in Abacus software. The model of this study is model used before. A straight line is drawn, which is used to observe where the convergence occurs. The trend line indicates that the starting mass size of 55 millimeter if the number of elements.
Sorry, Prayoda, we have. Let's move to the conclusion because the time is almost finished.
Oh, yeah. The conclusion, the result of the numerical validation shown that the similarity of the study with reference is 50%. The similarity can be influenced by different material inputs. In displacement control, propagation only occurs on the one side. This is because the structure only consists of the one component, so the direction of the stress does not fluctuate. The results of the mass convergence study show that the mass size of 55 millimeter is suitable for a future research. This is because 55 millimeter mass size has result that are not much different from the smaller size, but it has much smaller number of elements compared to the smaller size. That's all for me. Thank you for your attention.
Thank you very much, Prayoga, and sorry for my pronunciation of your name. We have no time for the other questions. I have the session is finished, and let's move to new session. The good news that it's time to change the chair from an agreement to a beautiful girl. My colleague is here, and see you. Bye. And I please, Sabrina.
Good afternoon, everybody. We can start with the section number 2. I would like to remember you that each speaker has a maximum time of 10 minutes, questions included. The first presentation is entitled Analysis of the idealized steel pipe under internal explosive loading, comparison between finite element approach and laboratory experiment. And it's presented by Maulana.
Maulana, yeah, that was me.
Okay, please.
Okay. Good afternoon, ladies and gentlemen. My name is Muhammad Iqbal Maulana. I am a student of 11 Maret University. Today, I will show you about my research with the title is Analysis of the Idealized Steel Pipe under Internal Explosive Loading, Comparison between FA Approach and Laboratory Experiment. This presentation consists of 5 chapters. The first is Introduction, Literature Review, Benchmark Reference, Result and Discussion, and close with Conclusion. This research was conducted to obtain a reliable finite element methodology in modeling internal blast loading on a designed steel pipe. The steel pipe referred to here is a pressure vessel. The pressure vessel is usually designed to hold gases or liquid at a pressure substantially different from the ambient pressure, where there is no formally recognized standard for the design of a pressure vessel. To accommodate explosive or impulsive load, which may result from the explosive or of highly explosive charge or the ignition of flammable gases. This previous study of explosive in pipeline was carried out by Ruston, where the data obtained from the experiment will be used to validate numerical and analytical model. Thus, this study will observe the failure mechanism of such a pipe when subjected to very high rate loading. The research will be carried out using simulation to improve the understanding of blast loading on structure in abacus CIA application. The following equations are some equations that have been made from previous studies that have been carried out from equation 1 to equation 7. Some various material and shape can be used as energy absorbing structure. Ruston used AP5LX42 steel pipe as constituent material. The specification of the steel pipes can be seen in table 1. The research conducted by Ruston at the University of Liverpool in figure 3 was used as reference in this research. A series of tests that have been carried out by Ruston were carried out on a steel cylinder without joints, open-ended, 80 millimeter long, 3 to 4 millimeter in diameter, 9.5 millimeter thickness, and the detonator was placed in the middle of an open-end pipe that was hung on trellis and sling thick with the constituent material of which are IP5L X42 metal pipes. Then in the figure 4, we can see in the modeling that we did in this study with Abacus CIE. The numerical simulation that is carried out focus on the value of the plastic hop strength of the pressure vessel when an explosive occurs. Pressure vessels are made using the Abacus CIE module. As shown in figure 5, the simulation model use only a quarter section because the pipe shape is symmetrical, and to make the simulation easier, the boundary conditions are located at the top and the bottom of the simulation model. At the top, the boundary condition is XS by mm, where is U1 equal UR2 equals UR3 equals 0, which means that the exposition in the simulation is locked. At the bottom, the boundary condition is YS by mm, where is U2 equals UR1 equals UR3 equals 0, which means that the Y position in the simulation is locked. In figure 6 is a comparison between the highest and lowest meshing used in the simulation, namely meshing 0.0025 meter and meshing 0.025 meter. The result of the simulation that have been carried out in figure 7 on the left side of the picture is a comparison between the comparison of the simulation result with a reference source that are not much different or harmonious. On the right side, the picture shows a comparison the contour plastic hoop strength that occur in a pressure vessel with a load mass of 0.6 kilogram TNT and 0.8 kilogram TNT with meshing 0.0025 meter. Here, the following is a comparison of the contour of the displacement value with a loading of 0.6 kilogram and 0.8 kilogram of TNT, and the maximum value for displacement of the structure with explosive loading of 0.6 kilogram are shown in figure 8, that is 0.01479 meter, and the maximum value for displacement of the structure with an explosive loading of 0.8 kilogram are shown in figure 9, that is 0.0247 meter. The following is the result of mesh convergence on strain and the displacement. Based on the convergent mesh data, beside, we can conclude that the most stable meshing from the mesh convergent data on the maximum plastic hoop strength and displacement occurs at 0.0025 meter until 0.0075 meter. In the conclusion, the comparison of a result with the reference source is not much different or harmonious. Then the percentage increase that the percentage increase that occur in the strain of the plastic circle with a TNT meshing loading 0.0025 meter is 61.77%. We get the percentage increase in data based on comparison of the final yield between 0.8 kilogram and 0.6 kilogram TNT, with the equation for the final plastic hoop strength 0.8 kilogram and 0.6 kilogram with the we get the percentage increase in data based on a comparison of the final plastic hoop strength of 0.8 kilogram and 0.6 kilogram TNT with the equation for the final plastic hoop strength of 0.8 kilogram TNT minus the final yield of 0.6 kilogram divided by the final plastic hoop strength of 0.6 kilogram TNT multiplied by 100%, and then the result obtained is 61.77%. As for the percentage of the maximum displacement value of the structure with a TNT meshing loading is loading of 0.0025 meter, which is equal 76.55%. We get the same percentage of the maximum displacement, same the equation before, and then for the percentage of the minimum percentage of the displacement is 0, because there is a no displacement that occurs in the simulation test result. And then the mass convergence data on the maximum plastic hop strength and displacement can be concluded that the most stable meshing occur at 0.0025 until 0.0075, and then the smaller of the meshing used in the simulation, the more similar or closer the final result will be. And then bring us to the end. I would like to say thank you for your attention and your time.
Okay, thank you for your talk. Any questions or comments?
I have sorry.
I have a quick question. Have been the tests performed according to a specific recommendation?
Excuse me, can you repeat the question?
Yes, of course. Have been the tests performed according to a specific standard or recommendation?
The test before is from the laboratorium, and then this test I use is from the simulation. So the data from the simulation before is nothing.
Okay, thank you. The next presentation is entitled Assessment of the Trapezoidal Corrugated Shear Wall, Comparison between Laboratory Experiment and Numerical Calculation, and is presented by Arianto.
Okay, anyone can hear my voice? And
Yes, I can hear you. And I can see your screen. You can start.
okay, hello, my name is Adrian Sabagus Arianto. I'm a student of mechanical engineering at Universitas 11 Maret. And in this session, I will explain about assessment of the trapezoidal corrugated shear wall, comparison between laboratory experiment and numerical calculation. And this is our content. For the first is introduction, purpose research, literature review, research methodology, result discussion, and then for conclusion. In improving the function, generally thin steel plate shear wall or SPSY added stiffener. However, SPSY with stiffener increases construction cost due to time-consuming factors and the high cost of welding thin plates. Therefore, thin steel as an infill was modified in the hope of increasing its capacity, but still having a low construction cost. And our purpose research is comparison result between experiment and numerical calculation with Abacus FEA on hysteresis for displacement graph, and then compare and observe experimental and numerical solution on displacement, stress, and strain. And for literature review on trapezoidal vertical corrugated steel shear walls in the experimental were made using the platform interaction or PFL method. Or ultimate strength vertical corrugated steel shear wall is obtained from equation 1. And then for interactive shear buckling of the infill corrugated panel obtained from equation 2. And limiting shear elastic displacement of the corrugated panel frame was obtained from equation 3. And the picture on the right is our model trapezoidal vertical corrugated steel plate shear wall in Abacus. Now for research methodology, previous research by Mami et al. 2013 Observe the behavior of cyclic loads on trapezoidal corrugated and unstiff steel shear wall specimen. During loading, the value of the applied load and the amount of displacement at the top of the specimen is continuously measured. The result taken from this study as material for validation are the result of the first displacement hysteresis on the second specimen, namely the trapezoidal vertical corrugated steel plate shear wall. And for our geometrical model, the trapezoidal vertical corrugated steel plate shear wall was itself consists of several parts. The first part of consists of bottom beam using the HEB200 specification with a length of 3,200 mm with 18 stiffener, and then at the top there is a beam with HEB140 specification with a length of 2,000 mm with a stiffener of 8. And the picture on the left is geometrical dimension of trapezoidal corrugated plate in millimeter. And then for the column, on each side, the infill have length of 1,650 millimeter using the HEB 160 specification and are given for stiffener. In addition, there are two triangular stiffener in each column. And finally, there is an infill plate with trapezoid shape in the center. And the picture on the right is trapezoidal vertical corrugated steel plate shear wall, our proposed design in millimeter. And then for material properties, the material used is in this study is steel, and then steel has a Poisson ratio of 0.3 based on research by MME et al. 2013. The materials mechanical properties are based on the coupon test based on ASTM EHM04, and it is stable our material properties for column, beam, and plate. And then we use isotropic hardening for the analysis in the influential properties of trapezoidal vertical corrugated steel plate shear wall. For inertial imperfection, the specimen is buckling analyzed, and then the first buckling shape mode is used in the FE model using keyword comment in the abacus. And for FE setting, well joined with this plate and bolts connecting to the infill plate are neglected, and we use my size is 25 millimeter. For the rigid support, we have U1 equal U2 equal U3 equal 0, and UR1 equal UR2 equal UR3 are 0. And on the top, we use cyclic plot with displacement and sum amplitude. And for result and discussion, for mass convergence from the first buckling load vector, convergence between mass element 120,000 to mass element 350,000. And then for general mass convergence from static general, stabilize between 18,000 to 90,000 mass element. And then judging from the PE echo counter or the picture on the right, the largest strain occurs in the infill plate. Compared with the reference counter, the damage to the infill plate is similar. A small difference is found at the top. A small difference is found at the bottom of the column, where the simulation results show more deformation. And then in the displacement counter, or the largest displacement counter, it is noted that the largest displacement also occurs in the infill plate. Its position is opposite close to the location of the greatest strain. There is a large displacement even at the location closest to the largest strain. Displacement because the other parts are full when displacement occurs, so that strain occurs at that location. Displacement also occurs in the beam and column on the left, because it is the same direction as the applied load. When view on the stress counter at the 0 steps, show the counter when the load has not occurred, so that no stress value appears. And then for the stress counter at 285 steps, there is an increase in stress that occurs in the infill plate area when loading continues. As we seen in stress counter at 1,140 steps, the highest stress occurs in the column and triangular stiffener. This happens because when the alternating loading takes place, the area experiences greater fatigue than other location, and it is proven that there is a large deformation in the area. And for hysteresis, or the picture on the right is comparison of force displacement hysteresis between FEM we study and pioneer experiment from Emami et al. 2013. From the picture, the result of hysteresis is often are quite close to the experimental result. The maximum shear force achieved in the experimental result is 500 kN. Meanwhile, in the simulation result, the maximum shear force is 504.52 kN. And for conclusion, mass convergence when element 120,000 until 350,000 in buckling analyzed, and convergence when element 18,000 until 90,000 in stress static general. Compared with the reference contour, damage to the infill plate is similar. The hysteresis generated by the simulation is quite close to the experimental result. The maximum shear force achieved in the experimental result is 500 kN. Meanwhile, in the simulation result, the maximum shear force is 504.52 kN. The biggest displacement also occurs in the infill plate. Its position is different from the location of the largest trend. And the last is recommendation that can be made for future research are to vary the geometry and material used from the infill plate to find an attractive steel plate shear wall or SPSY which can withstand earthquake lateral loads better. Thank you.
Thank you for your talk. Any questions or comments?
I have a question. Did you consider different shape for the corrugated shear wall besides the trapezoidal one?
For the different shape, we will use in our next research, not from not in there, not in here.
Okay, thank you.
Thank you again. The next presentation is entitled Crashworthies of Cross-Sectional Hollow Tubes Filled with Concave Hexagonal Under Compressive Load using Nonlinear Finite Element Analysis, and is presented by Metanadi.
Yes, thank you.
Perfect. You can start.
Hello, everybody. My name is Andre Hacawan Metanadi. I'm from 11 Maret University in Indonesia. And today I bring my topic. The title is Parametric Study of Cross-Sectional Hollow Tubes Filled with Concave Hexagon. Now, under compressive load using nonlinear EV analysis. The topics is divided into 6 subtopics. They are general concept of the topic, introduction, literature review, research methodology, result and discussion, and conclusion. For general concept of the topic, during a collision, the vehicle occupants are subject to a number of forces that can result in injury, including rapid deceleration and rapid acceleration, depending on the direction of impact in the collision. An effective crashworthy vehicle design will distribute this injurious force over as great a period of time and distance as possible, including by directing them to parts of the body that are more capable of withstanding them. And we can look at illustration of crashworthiness in car in the right picture. For the introduction, crashworthiness is the ability of a structure to protect its occupant during an impact. Much research has been done to improve the performance of crashworthiness. Kim et al. In 2022 proposed a new multi-cell block configuration by optimizing the distribution of block elements in corners. The results show that the crashworthiness of the new multi-cell profile is nearly double that of the original structure. This research, numerical validation, and mass computing study were carried out for the improvement of concave hexagonal multi-cell crashworthiness under axial compression. For the literature review, higher energy absorption efficiency of material, or SEA, is shown from higher specific energy absorption, as seen from equation 1. Specific energy absorption is derived from the calculation of absorbed energy per unit mass of the structure, where IM and EA represent the total mass and energy absorption of the cylinder respectively. The rate of transfer of the energy absorption process is determined according to the energy efficient method. It can be seen from equation 2, where eta G represents energy absorption efficiency. In addition, the mean crushing force is analyzed as the average energy absorption experienced by the material. It can be seen in equation 3. research methodology, geometrical model, a concave hexagonal structure as auxiliary elements in the cylindrical shell as shown are distributed along with the circumferential and radial direction of the cylindrical shells, which are connected by circular arcs. The inside diameter and the outside diameter are represented by d and d capital respectively. The coefficient alpha is used to express the ratio between the two geometries. Alpha equals to d per d capital. The number of concave hexagons in the perimeter and the radial distribution is denoted by x and y respectively. The cylindrical shell has a uniform thickness distribution with p equal to 1 millimeter. The section parameters alpha, x, and y are 0.5, 0.6, and 2 respectively. The cylindrical shell has an axial height of 150 millimeter and an outer ring diameter of 60 millimeter. For the boundary condition, as shown in the picture below, we name our specimen as shield 1. The upper surface of shield 1 is compressed by the moving rigid wall at an angle of 0 degree. The mass of the moving rigid wall is 600 kg. The subsurface of shield 1 is restricted to the fixed end. For the upper part, there is a horizontal buckling displacement boundary condition. The loading speed given for the FE model from shield 1 is 15,000 millimeter per second axial, and the element size given is 1 millimeter, and the time step in the simulation is 8 milliseconds. For the material we use in the study is aluminum 60614, where the mechanical properties of aluminum 60614 and the stress strain curve as well. For research validation based on a study conducted by in 2022 for the design of a new bionic bandit tube for several combustion board cases, the FE model was verified using a universal testing kitchen. The test specimen is named as BBT1. The actual combustion experiment of the aluminum cylinder tube was tested by a universal testing kitchen with a measurement range of 300 kilonewton at room temperature. The BBT1 specimen is placed on a rigid plate and compressed by the plate at a compression rate of 5 millimeters per minute. The result taken from this ID as material profile validation is post-displacement hysteresis on main specimen, namely BBT1. And for the result and the discussion, in the deformation progressive picture, as we can see in the left picture, the deformation progress between BBT1 in the upper and the C1 in the bottom looks very similar by each step time. And for the graph in the right picture, we can see that the simulation pattern, black color, benchmark simulation, blue color, and the experiment, green color, quite similar by the pattern we obtained from. And the mean crushing force between numerical red color and the mean crushing force of experiment purple color are squeezing each other in the time of value. And here the plastic strain contour and von Mises contour. From the stress and strain contour, we can see that the displacement are equally distributed in specimen body. And from the lobes created by either experimental in the left and the numerical result in the right are the same, creating 8 lobes. And here the mass convergence study of displacement and energy absorption in the right. From these two pictures, we can see that the mass convergence happen in a mass element size of 1 millimeter. And for the conclusion, mass convergence was obtained at energy absorption values of 8.17 kilojoule per kilogram and displacement of 115.552 millimeter with a number of elements 93,148. The crushing force obtained was 92.38 kilonewton and the mean crushing force obtained was 79.9 kilonewton. The contour formed in the simulation result has shown that the deformation of C1 is actually regular and the most deformed part is the surface close to the contact of the moving rigid wall. The lobes formed from the numerical result are 8 lobes, some as the lobes obtained from the benchmark numerical. Energy absorption obtained tend to be stable when reaching element 23,402. I think that's all for my presentation. Thank you for your attention.
Thank you for your talk. Any questions or comments? I have just a curiosity. How much is the computational cost for this type of simulations?
I'm sorry, can you repeat it?
I have just a curiosity. How much is the computational cost for this type of simulations?
How long it takes?
Yes.
It's about 9 hours, dependent to the thickness. But I took usually 10 or 12 hours.
Okay. Thank you. Thank you again. We
Okay,
can
thank
move.
you.
Thank you. We can move to the next presentation. The next presentation is entitled Fatigue Damage Prediction of CFRP specimens by means of non-destructive techniques, and is presented by Saponaro. Please,
Yeah,
Andrea.
Okay. Can you see my screen?
Yes, yes.
Yeah, okay. Hi everyone, I'm Andrea Saponaro, a PhD research fellow at the University of Salento, Italy. Electrical resistance and thermographic measurements for the investigation of fatigue damage are the subject of this research, fatigue damage prediction of CFRP specimens by means of non-destructive techniques. Fatigue damage is the Fatigue damage is the most important failure mechanism that occurs in critical components, and the evaluation of the structural integrity for the entire service life is an important challenge to be achieved. In this research, electrical resistance and thermographic methods were used to monitoring in real-time fatigue damage on a batch of CFRP specimens with different load conditions. The year results were compared with the processed thermal data expressed to appropriate damage parameters to study the possible correlation in the prediction of fatigue damage. So, composite specimens in CFRP considered for fatigue damage monitoring by ERC and infrared thermography measurements are manufactured using the liquid resin infusion process. The test specimens consist of 6 layers with the second sequence of 14.5, meaning 45, 0, 19 to symmetrical. Before performing the test, a static tensis test was carried out on a displacement control on an instrument machine with a velocity of 0.5 millimeters of minutes to evaluate the ultimate fracture load, taken as a reference for the subsequent tests. Regarding resistance measurements, a no continuous direct current of 0.1 milliampere was injected into the specimen through 2 external contacts, while the resistance is determined by measuring the voltage drop between the 2 internal contacts in the classical 4Y configuration. So the experimental equipment include a DC power supply generator and a digital acquisition unit as shown in figure. Before fatigue tests, isolating tabs were built and bonded to the end of the specimen around the gripping area to isolation the specimen from the testing machine. The internal contacts in copper tape for the electrical resistance measurements have been positioned at a distance of 53 millimeters, while the external contacts for the injection of current have been positioned at the end of the specimen. In the electrical circuit, we can see RC is the parasitic resistance due to wires and electrical contacts, while RS is the resistance of the specimen. Regarding the thermographic setup, the specimens were monitored during fatigue using a flare infrared camera equipped with a microbolometric sensor. The surface of the specimen was painted with high temperature matte black paint for thermal analysis. The thermal sequence were required at regular intervals of 5,000 cycles with high resolution, frame rate of 100 Hz, and acquisition time of 10 seconds. A damage parameter has been proposed by the author in this study, where T0 is the absolute temperature at medium load detected in the initial conditions. The two terms of equation are related to the chosen region of interest, ROI, damaged and undamaged respectively. at a given instant of the fatigue life. Fatigue tests were performed in tension-tensor load with a sinusoidal waveform, frequency of 10 Hz, and stress ratio of 0.1. On all parameters are summarized in the following table. The effect of the electromechanical response was also investigated. The resistance change due to temperature can be calculated with the following equation, where A is the resistant temperature coefficient, which is depending by the material initial temperature and geometry, while delta T is the temperature different from the starting point. The computed electrical resistance data due to thermal contribution have been subtracted from the recorded value due to experimental resistance in order to obtain the resistance value due to only damage. So the term A was experimentally measured heating the specimen by means of an halogen lamp and record in real time voltage and temperature data of the thermocouple both in the heating phase. So the electrical resistance data were average over a time interval of 22 seconds. In the following graph, there is two important information. From about 30% of the fatigue life, the resistance increases due to early nucleation of the damage. Starting from about 16–70% of the fatigue life, the electrical resistance show a further rapid increase in the damage propagation phase before the sudden failure of the specimen of the sample. This results is in agreement with the rapid stiffness degradation. This video, not to move you, show the damage propagation before the final fracture of the sample. The process, the thermal data expressed to the dissipative damage parameter, this generally showed for specimen A3 and A6 a similar trend to the stiffness degradation expressed to the decay parameter. The data show that the increase of the damage parameter is in agreement with the observed increase in electrical resistance in the range from 5–30% of the fatigue life. Starting from about 16% of the fatigue life, the trend of the dissipative parameter and the resistance both show a rapid increase. For a five specimen, starting from 16% of the fatigue life, the general trend of the thermal profile decreases due to the considerable damage of the composite surface, which determines a reduction in the temperature in the selected ROIs, while in this phase, the resistance show an increase as observed. In conclusion, from the ER results, a slight reduction in resistance was observed in the initial phase of the test. Subsequently, the resistance value show a rapid increase from about 5–30% of the fatigue life due to the early nucleation of the damage, of the delamination substantially. Starting from about 16–70% of the fatigue life, the electrical resistance show a further rapid increase in the damage propagation before the fracture, in agreement with the stiffness degradation of the test samples. The processed ER data for specimen A3 and A6 showed that the increase of the damage parameter is in agreement with the observed increase of electrical resistance in the range from 5–30% of the fatigue life. Subsequently, starting from 60% of the fatigue life, the trend of the dissipative parameter and the resistance both show a rapid increase. This latter result is in agreement with the stiffness degradation expressed through the decay parameter. For a 5 specimen starting from 60% of the fatigue life, the trend of the dissipative parameter decreased due to the effect of the considerable surface damage of the composite, which determined a reduction of the temperature in the choice region of interest, while in this phase, the electrical resistance show a further rapid increase. Thank you very much at all for your attention. Okay.
Thank you for your talk. Any questions or comments?
Yes.
Please.
Do you think that the stress ratio influence the fatigue behavior of your test? You work with stress ratio 0.1, right?
Yeah, the stress ratio applied for the fatigue test is 0.1, 0.1, but we have not make the other stress ratio for the tests.
Okay, but do you expect
still to be investigated?
Influence?
Yeah.
Yeah. Okay.
Sorry, excuse me.
Okay.
Thank you.
Thank you again. The next presentation is entitled From Point Cloud Data to Structural Modeling, the case study of the Tusk at Spiny Palace, Scotland, and is presented by Marinelli.
Thank you. It seems that I cannot share my screen. Yeah, right. I should be able to share it now.
Perfect.
Great,
Okay,
thank you. So good afternoon, everyone. I will be taking the next 10 minutes to talk about a user-friendly approach to creating three-dimensional finite element models utilizing point cloud data for structural engineering purposes. And this is a research project supported by the Conservation Directorate and the Digital Documentation Team of Historic Environment Scotland, while it's funded by Edinburgh Napier University. Scotland's historic environment is an essential part of the country's cultural background and its economy. And the country is often referred to as a nation of stone, typified by its historic masonry buildings and castles that form one of the richest legacies of traditional and historic structures in the United Kingdom. So some of these are internationally iconic structures of historical and cultural heritage, and either in remote areas or in the major cities, there are excellent examples showcasing the use of natural building stones as a construction material. Scotland is world famous for its castles, not just because so many are immaculately preserved, but also because many are set against some of the most breathtaking scenery in Britain. So since 2017, the Scottish government has worked with Historic Environment Scotland, which is the lead public body established to investigate, care for and promote Scotland's historic environment, to develop a long-term infrastructure investment plan for restoring, enhancing, and conserving the built heritage. As part of this, their digital documentation team undertook the mission to digitally document every place and object in their care through the RAY project. The development of digital technologies such as terrestrial laser scanning has already helped produce accurate representations of structures with applications in conservation, monitoring, and building information modeling. But the exploitability of laser scanning outputs in the form of point clouds is still challenging with respect to the application for structural analysis of historic buildings. The project seeks to explore the procedural options for the development of numerical models for structural purposes, linking available three-dimensional point cloud data to commercial structural engineering software to enhance analysis options for historic masonry structures in the care of Historic Environment Scotland. So this research was based on a topic of common interest between our university and Historic Environment Scotland, having as a case study a freestanding 6 meters high block of masonry referred to as the Tusk, which is at spiny palace at the north of Scotland. So it appears as an isolated pillar and forms the only upstanding remains from a 15th century load-bearing curtain walling that has considerable archaeological significance. It was chosen as an example of a very irregular structure in need of intervention to demonstrate a pilot process for creating a three-dimensional solid mesh compatible with commercial engineering software, while at the same time using simplified material laws and boundary conditions to allow for a first stage structural assessment. Processes necessary to simplify and reconstruct the three-dimensional mesh model from point cloud data were performed, with operations comprising the point set simplification and the cleaning of data and surface reconstruction to create a thin watertight mesh. The open source tool MeshLab was used for the application of appropriate filters to approximate noisy data and produce smooth, robust surfaces with points that are uniformly distributed. The thin mesh was used as the basis for the creation of a three-dimensional solid structure in SolidWorks that constituted input compatible with finite element commercial software, such as Abacus or ANSYS. ANSYS workbench was used in this case, with the resultant model balancing computational cost and accuracy with respect to the needs of this project. Masonry was modeled using a continuum homogenized approach, implicitly considering the effects of mortar joints. And the wall is made of sandstone blocks bonded with lime mortar and arranged in random patterns. So that led to the assumption of a simplified composite material behavior, adopting values of mechanical properties from relevant literature. The wall was considered as fixed at its base, and combinations of self-weight, live load, and wind loads appropriate for that area were considered and applied for evaluating the task's structural performance, the structural response to a range of reasonable loading conditions under static analysis. So given the current condition of the task, results were interpreted by means of macroscopic examination of displacements and a safety factor, considering combinations of stresses based on a Moore-Coulomb failure criterion. Results confirm on-site observations from Historic Environment Scotland that the task shows signs of instability and sways when loaded laterally. With the analysis assumptions considered, the stress combination for failure would be exceeded in large parts of the structure, although examining closely how this develops over the incremental application of the load combination, this does not happen before reaching about 85% of the total design load. The whole project verified the pilot process for using existing point cloud data for structural engineering applications and confirmed the compatibility of numerically observed vulnerable areas with the existing failure patterns. Indeed, critical load combinations lead to stress patterns in accordance with the location of vulnerable areas with visible signs of deterioration on the real structure, exhibited mainly as diagonal cracks and splitting of joints. Having completed this pilot project, areas of further research comprise evaluation of the potential of advanced material laws for masonry, alterations in the mesh generation choices, and consideration of alternative boundary conditions, including the current state of the structure's foundations and existing defects. The project was valued by all partners involved for its larger scale potential to improve structural monitoring strategies and to lead to more targeted interventions as needed. Thank you for your attention, and I'm happy to get any comments or questions if we have the time.
Thank you for your talk. Any questions or comments? I have a question. Can you give more details on the macrostructural approach that you use in your model?
So the masonry was in a bad condition, so it could not be accurately estimated. So I collected data from the actual material that was used on that structure, although the vulnerability and the weathering conditions could not have been quantified. And then I compared that with guidelines from the literature, as well as the Italian building codes, which were a good source of information. And then the values were approximated, and we took a range of values anyway to be able to have a reasonable estimation of the mechanical properties.
Okay, thank you. Thank you again. We can move to the next presentation. The next presentation is entitled Dynamic Computational Analysis of Pentamode Structures, and is presented by Limperopoulos.
Yes.
Correct?
How are you? Huge name, I know. So,
okay,
hi.
You can start.
I am Panagiotis Limperopoulos, and I'm going to present to you our analysis, our research dynamic computational analysis of Pentamode structures. My co-author is Estathio Theotokouliou. And we are in the Department of Applied Mathematical and Physical Sciences in National Technical University of Athens. So, in this presentation, we are going to see a brief introduction over metamaterials, the numerical investigation, the results, and we're going to discuss them, and finally the conclusion. So, what are metamaterials? Metamaterials are materials with extreme properties not found in natural materials, like the negative Poisson ratio, the negative electric and magnetic coefficient. They can have programmable properties, and they are a subcategory of the composite materials. There are several types of mechanical metamaterials, like the auxetic metamaterials, the negative compressibility metamaterials, and the Pentamode metamaterials. The auxetic metamaterials have below the zero Poisson ratio, while the negative compressibility appear to decrease their size after tension and increase their size after compression. And finally, the Pentamode metamaterials, which are the one that we're going to see. I have also included at the bottom of each slide our references, where are we taking everything from. So pentamodes are 3D lattice structures which are composed by rods, and they have low values of the ratio G to K, where G is the shear modulus and K is a bulk modulus. Because they have low values of the ratio G to K, they are also named as solid water. They can be used for seismic isolators and generally for vibration isolation and in bioengineering applications. Here you can see a typical pentamode union cell, where D capital is a large diameter, D small is a small diameter, and A is the main dimension. Here you can see how we can fabricate them. We can fabricate them using 3D printers. As you can see, we can do in each dimension that we want. In this presentation, we are focusing on seismic waves, which are propagated through the Earth's crust, and they have frequency between 0.0 Hertz to 10 Hertz. And the most catastrophic phenomena are between 0.01 Hertz to 2 Hertz. So the numerical investigation. Here you see some pedamode structure that we have used. This is a more technical, a more artistic approach as you see them, because we analyze them through a finite elements method using 3D beam elements. And as you can see, we have used 3 union cell towards x-axis, 1 towards y-axis, and we have used 1 layer, 2 layers, 3 layers, and 4 layers with and without confinement plates. We have used as material steel with those properties. And now we are going to see the convergence of the algorithm. We have used this type of pedamode, which has 60 millimeters. We have fully constrained the bottom nodes. We have constrained the z-axis displacement at the top nodes, and we have applied a force of 1.5 kilonewtons toward the x-axis at the top nodes. As you can see, the displacement we have increased from 1 element to 15 elements per rod. And as you can see, we have the same displacement at the top nodes. So the algorithm is converged, and we have used 4 elements per each rod. Now the results. At first, we will see a dynamic shear strength versus a static shear strength calculations. We have a pedamode, as you can see here, with steel as material. The main dimension is 30 millimeters, and we have applied a displacement at the top nodes of 1 millimeter, and we have fully constrained the bottom nodes. And the frequency range from 0.01 Hertz toward to 10 Hertz. As you can see, the dynamic shear strength appears to decrease, but this decrease is considered significantly small. Now we will see some cases that we have tested. At first without confinement plates, and then with confinement plates. We have calculated the shear strength and the bulk strength for the 4 cases of height, of pedamode height. Yes. And now you see the shear strength. As you can see, the pedamode with NZ1 appears to have the higher value for the shear strength, and we have a discrepancy for the pedamode with NZ4. Now the results for the bulk strength. We have the highest value for the bulk strength for pedamodes with NZ1. And these are the results for with confinement plates. As you see, as we have smaller values for the NZ, the shear strength appear to have increased value. We see that the 2 discrepancies for the NZ3 and NZ4, the values are the same as with the previous case, without confinement plates, but for the NZ3, we have an increased value, so we cannot see very well what's going on. But if you see the values, they are very close. And these are the results for the bulk strength. We see that for NZ4, we have a decrease in bulk modulus, but it's considered small. And now for a thinner pentanode, we have, as you can see, the values for the shear strength is lower than previously, and we see more discrepancies than the previous case. And these are the results for the bulk modulus. Now the results with confinement plates. As you see, the results are very high for the discrepancies. That's the reason you see the values of the shear strength so low. And these are the results for the bulk modulus. So we have tested different loading frequencies with and without confinement plates. And we see some discrepancies after the third layer, as you can see. After NIZ 3, we have discrepancies. The shear strength and the bulk strength decrease its value as the NZ gets higher. And if we have thinner rods, the values for the bulk modulus and shear modulus, shear strength, have lower values. And we have more eigenfrequencies that we can see. The eigenfrequencies are the discrepancies. As future work, we are going to test more materials, more pentamode topologies, and also rod geometries. And this is our bibliography. And thanks a lot.
Okay. Thank you for your talk. I'm very sorry, but we haven't time for question or comments, and we have to move to the next presentation.
Thanks.
Thank you again. The next presentation is entitled Stress-Assisted Corrosion of Toroidal Shells, and is presented by Pronina.
Yes, our report will be presented by me. I'm Alexander Ilyin. So
Perfect. You can share your screen.
Yes, just 1 second. Yes, can you see my screen now?
No.
Not yet?
Not yet.
Excuse me, just, yes. Yeah, and now here it is.
Okay.
Ladies and gentlemen, good afternoon. My name is Alexander Ilyin. I'm a first-year PhD student at St. Petersburg University, and I would like to introduce our report about stress-assisted corrosion of a toroidal shell under pressure. Let us start with some words about applicability of toroidal shells in engineering. Toroidal shells find many engineering applications, ranging from fuel tanks on rockets to turbine shrouds. Pipe bends and elbows, it is an important part of every piping system, and it also has the shape of the torus. All of the above structures are subjected to the action of mechanical loads and the aggressive action of gaseous, liquid, and solid media, such as water, fuel, gas, and so on. Simultaneous action of mechanical loads and aggressive environments can cause mechanochemical corrosion. The term mechanochemical corrosion was introduced with regard to general corrosion facilitated by stress, to be more precise, for anodic dissolution of elastically deformed metals. Corrosion may be defined as a general dissolution of the material with a rate V proportional to the maximum normal stress at a corresponding point of the inner surface. It can be described by formula presented on the slide. Here A and M are empirically determined constants of the corrosion kinetics. In our study, we consider moderately non-uniform wear when we can neglect the change in the normal or to the corroding surface. This slide shows the general view of the geometry of considered toroidal shell. In our study, we consider the linearly elastic thick-walled shell under internal pressure. Here R is so-called distance parameter, which is describes the distance between the torus center, axis of revolution A, and the tube center. In our study, we consider the two-dimensional axisymmetric problem for the cross-section of the torus loaded with a constant pressure on the involving internal boundary. Let us move to the model. The left-hand side presents the formulation of our finite element model. The problem is reduced to the two-dimensional axisymmetric problem for the cross-section of the torus loaded with a constant pressure on the involving internal boundary. In order to solve the boundary value problems with the priori unknown boundaries, the new APDL code was created and launched with via the ANSYS finite element software. The choice of the time step must be in agreement with the chosen step in space, or the mesh size, actually. Calculations were carried out for various time and spatial step sizes to ensure the obtained solution is mesh insensitive. This graph shows the growths of first principal stress at different nodes, actually marked by points with numbers, on the inner surface of the toroidal shell cross-section with time. As one can see, the greater the value of angle phi is, the higher is the first principal stress. The smallest stress is observed at 5 phi equals 0 degrees, and the largest at the 5 phi equals 180 degrees. It can be concluded that the service life of the toroidal shell is to be determined by the thickness and the stress value at this point, at point 61. In further analysis, we will analyze the stress growth at lifetime and lifetime at the point 61. This graph shows the growth of the first principal stress at the node of our interest for various distance parameters R with time. Other parameters being equal, it can be noticed that the lower the distant parameter is, the higher is the rate of stress growth. From the presented graph, we can observe that for sufficiently large distance parameter, the results tend to the solution for a cylindrical pipe or perfect tube. Actually, let's go further. This graph shows the dependency of the service life of the toroidal shell on the initial relative stress, related to the ultimate stress, actually, for different pressures. Various values of the initial stress for each curve were obtained by variation of the initial stress thickness, other parameters being fixed. As one can see, at stress ratio equal to the constant value, a toroidal shell loaded with a higher pressure has a greater lifetime. This is due to the fact that in these conditions, shell under the higher pressures have a greater thickness. And it is also necessary to add something about the instability of solution. Relatively strong non-uniformity of the stress distribution leads to localization of the corrosive wear when the chosen model of the corrosion kinetics doesn't hold. Localization of corrosion is sufficiently thick wall shells occurs before any of the critical conditions, I mean reaching the maximum allowable stress or the minimum allowable thickness is met. Let's go to the conclusion. The service life of toroidal shell should be determined by the dissolution of the wall in the vicinity of the points closest to the shell axis. As the solution for the toroidal shell tends to the solution for a cylindrical pipe as the distance parameter R of the torus increases and other parameters being the same. It was observed that at an fixed initial safety coefficient, a toroidal shell loaded with a higher pressure has a greater service life due to the fact that under such conditions, shell under the higher pressure have a greater thickness. And also, again, some words about non-uniformity of stress distribution, which leads to the localization of corrosive wear when the chosen model of the corrosion kinetics doesn't hold, and about localization of corrosion, which is insufficiently thick wall shells occurs before any of the critical conditions is met. Thank you for your attention. I'm open to your questions.
Okay, thank you for your talk. Any questions or comments?
Yes.
Please.
And your corrosion model, you have not introduced temperature. Now, temperature is a main parameter to estimate the life in the corrosion. Do you expect to introduce this parameter?
Actually, some additional values which can influence, which can make influence on our corrosion process are included in our constants of corrosion kinetics A and M, which is described in the literature. So in our study, we consider only the mechanochemical aspects. I mean, mechanics, stress, and chemical part is included in, and actually temperature too, included in our constants of corrosion kinetics.
Okay, thank you.
Okay, thank you again.
Thank you very much.
Okay, the next presentation is entitled Welding of Two Dissimilar Polymers, UHWMP using friction stir welding and evaluation of the mechanical properties, and is presented by Almaraz.
Yeah, can you see my presentation?
Yes.
Okay, let's start.
You can push the button on the right hand side, presentation mode.
Okay.
Is the button, yes, move on the right? Yes, this button.
Is right?
No, wait.
Thank you. From the beginning, thanks to Professor Iacovello and Di Cocco for their kind invitation to participate to this Congress. Now let's present the welding of two dissimilar polymers, ultra-high molecular weight polyethylene and PP polypropylene using friction stir welding and evaluation of mechanical properties. I come from the University of Michoacán in Mexico. Then the online, this introduction, material and experimental setup, raw material, experimental setup, testing condition. And the second part is friction stir welding of dissimilar ultra-high molecular weight polyethylene and polypropylene. Result of welding, tensile and hardness test, flow during friction stir welding, and finally conclusions. Now, the introduction, some main mechanical and physical properties of this true thermoplastic. Melting temperature for the polypropylene is about 113, 171. And for ultra high molecular is 144, 150. The glass transition temperature is very low for both thermoplastic, minus 34, minus 10, minus 80, minus 50. Density is quite similar, typical for thermoplastic materials. Viscosity for the first one is 2000, for the second one, 4500. Tensile's modulus of elasticity is quite similar, ranging from 1.3 to 1.8 for the polypropylene, etc. Ultimate tensile strength, 34, 40 for the first one, 39, 48 for the second. And finally, molecular weight. Here we have a high difference. For polypropylene, we have 280, 2,800, 7,100, but for ultra high molecular weight polyethylene, we have 2 millions and 6 millions of value. Typical application of these polymers for polypropylene is flexible and rigid packaging, and mainly is the automotive industry, high application in this field. And for ultra-high molecular weight polyethylene is characterized by high wear abrasion, high wear abrasion resistance, toughness, and biocompatibility. Now, the interest is to combine these two thermoplastic materials in order to see the potentiality of automotive industry. The experimental setup plates of ultra-high molecular weight polyethylene and polypropylene were machined in order to carry out friction stir welding. The pin profile used is 55 millimeters in length, and the profile is a hexagonal profile with 10 millimeters in depth and 9 millimeters in width. You see here the two plates of ultra-high molecular weight polyethylene and polypropylene. The color is quite similar, in fact. In order to improve the welding process, we introduced a stationary shoulder, which is contained in a bearing, the bearing in an aluminum plate, allowing to rotate only the pin, and the shoulder is a stationary shoulder. Here the first results. Picture 1 shows the friction stir welding process without a stationary shoulder. It's a rotating shoulder, and the welding is quite poor. In the picture B, we have the stationary shoulder, and the process of welding is improved greatly. Then, this is the testing conditions. Nomination were seen like 11, 12, meaning that we have 1,100 RPM and 12 millimeters in advances speed. The first one is rotation speed. All the specimens were tested in penetration speed of 5 millimeters per minute. All the pin profile were hexagonal, and some of the specimens were testing with preheating and without preheating. In these conditions, for example, the nomination 3000 means 3025 means 3000 RPM and 25 millimeters in advanced speed. Now, concerning the results, we have different results. The best results were concentrated without preheating, and for the lowest values of rotational speed, that means 1100 and 12 millimeters per minute in advanced speed. Now, the tensile tests were carried out following the STM standard D638 in order to fix the dimension of tensile specimen. On the upper side, we have polypropylene, and the lower side we have the ultra-high molecular weight polyethylene. Always the advanced speed was located in the higher density of this thermoplastic. Now we have the results for tensile test. The first tensile tests were carried out on the parent material. In the left side, we have the ultra-high molecular weight polyethylene, which presents an somewhat ductile behavior, but fracture in one point of elongation. In contrast, we have the polypropylene, which shows ductile behavior for a level of applying stress, which means a higher value for ductility. Now, the fracture test, the high values for the tensile test was related to the lowest values concerning rotational speed and advanced speed, and particularly without preheating. And here we have the hardness test along the specimen. In the left side, we have the parent material polypropylene, and the right side, we have the parent material for the ultra-high molecular weight polyethylene. And in the middle, we have the stir zone characterizing by hardness decrease, and the high value of hardness is for the nomination 1112. That means the lowest values for advanced speed and for rotational speeds. Finally, the flow during friction stir welding. All specimens present brittle fracture for all the combination of testing conditions, but concerning the flow, the vertical axis shows the tool pin's temperature in Celsius degree, and in the horizontal axis, the different nomination or specimen. You can see that for the lowest values of rotational and advanced speed, we have the lowest values of the tool temperature, and then we observe a laminar behavior of flow inside the testing specimen. When we increase the rotational speed and the advanced speed, a transition for turbulent flow is observed. Then, in conclusion, best results for joining were observed for a specimen without preheating and lower values for transverse and rotating speed. At the origin of this behavior may be lower glass transition temperature of these two thermoplastics, which led to adequate molecular diffusion in liquid state and mixing of the polymeric chain without need of preheating. Tunnel effect and microporosity were not observed for a specimen destined to tensile test. The decrease on tensile strength for the similar joining may be related to excessive heat generation during the welding process. Brittle fracture was predominantly welded specimen over the ductile fracture. Transition from laminar to turbulent flow leads to decreasing in tensile strength. Nevertheless, brittle behavior was observed for all testing the similar joints. Glycohardness values were obtained along the stir zone. By neighborhood in the stir zone, these values decrease as a consequence of material softening induced by heat regeneration and low heat dissipation in thermoplastic with low heat conductive properties.
Sorry?
Hardness values, yeah.
I have
Is
to
finished?
stop your presentation. Okay.
Okay, finish. Thank you for your attention.
Thank you for your talk. We haven't time for questions, and I have to move to the next presentation. Thank you again.
Thank you.
The next presentation is entitled Numerical Estimation of Peel Strength of Adhesive Joints via the Floating Roller Peel Test, and is presented by Arce. No. Isidro Arce? Yes?
Yes.
Okay.
Hello.
Please, Professor Almaraz, yes, close your sharing, please.
Okay.
Okay, thank you. Can you close your sharing, please? Okay, perfect, thank you. Can you share your screen? Perfect. Now I can see a black screen. Perfect, perfect. Okay, you can start.
Thank you. Thank you very much. Good afternoon to everyone. My name is Isidro Sanchez. I'm going to present on behalf of my colleagues, Joan Nóbrega, Raúl Campillo, and Paulo Novoa. The title of the presentation is Numerical Estimation of Peel Strength of Adhesive Joints via the Floating Roller Peel Test. This work was done in the Polytechnic of Porto, in the School of Engineering, and at INEI in Porto, Portugal. The outline of the presentation is introduction, objectives, experimental testing, numerical analysis, and conclusions. Adhesive bonding allows the assembly of dissimilar materials. With the development of non-metallic materials, this has become more employed in manufacturing. It's well known that adhesive joints are stronger when loaded in shear than when loaded in peel. Hence, the former is the preferred loading mode. However, applications like those in the aircraft industry, for example here, or maritime industry, require joints loaded mostly in peel. In consequence, the peel behavior and peel strength for the required substrate and adhesive combination have to be determined. The characterization of the peel behavior of the adhesive joint can be obtained through one of several experimental tests. In this case, we are focusing on the floating roller peel test, which is standardized both in the ASTM and the ISO. On the other hand, numerical modeling of bonded joints allows for predicting mechanical behavior of the joint. However, although experimental data indicate that bending of the thick adherent has also an effect in the peel strength, the current modeling techniques or current
modeling methodologies doesn't take in account that effect. So in this work, we aim to experimentally characterize one epoxy-based ductile adhesive, the Araldite 2015, and develop a numerical methodology to predict the peel strength of these joints using experimental data from the literature obtained from bulk and task test or thick adherent shear tests, employing the finite element method and Quasi-Pson modeling. So starting with the experimental testing, we use the adhesive Araldite 2015, which mechanical properties are were obtained previously, and they are already available in the literature. Tensile properties were obtained using the bulk test and following the appropriate standards, and the shear properties were obtained using the thick adherent shear test. In the case of the substrates, we are following the ASTM D3167 standard. So the adherents were cut from aluminum sheet. The material was from the series 6000, and the dimensions are shown in the screen. The specimens were manufactured or fabricated following the standard practices for these applications. So sanding, bonding, and these once the specimens were fabricated, they were left to cure for a week. Then we tested each one of the specimens using a universal testing machine with a 10 kilonewton load cell at room temperature with a testing speed of 125 millimeters per minute, and they were tested until failure, as shown in the little video or GIF in the screen. We can see the behavior of the joint during the test, which is what we want to replicate with the model. Here we have the results from the experimental test. We can see that we have a good agreement between the 4 cases tested for this adhesive, although one of them is slightly higher, but overall they are quite similar. The numerical test, the numerical modeling in this case, follow this summarized methodology, which will be explained in the following slides. First, we create the geometry following the standard, as mentioned before. Here, as we saw in the video before, the angle of the substrate changes through the test. So for that reason, we consider the 2 floating rollers and the center of rotation. We align the flexible adherent with the center of rotation of the rollers, and then we model the whole geometry following these constraints. Then the rollers were constrained to the center of rotation using beam elements. As well, the position between the 2 rollers was kept using another beam connector. Therefore, it will represent the actual testing device used. In addition, contacts were defined between the lower face of the flexible adherent and the left roller, and the lower face of the rigid adherent and the right roller. For the mesh, this was interesting. We use 3 different element types. First, we use cohesive elements in the bond line or in the adhesive layer because we're interested in obtaining the joint strength. So Quasi-Pson modeling is a good approach for that. For the flexible adherent, which is the one who is deforming through all the tests, we use 4-node solid elements. And for the rigid adherent, we use a combination of 3-node and 4-node solid elements. In this case, we kept a small element size close to the boundaries of the adhesive layer and where the right roller contact the substrate. In the top part, we use a coarser mesh to save some computational time. The boundary conditions represent those imposed in the experimental testing, as shown in the figure. And here we have the force displacement curve from the numerical test. This is for one particular adhesive. We did this for a few, for 4 adhesives in total. But we can see that in this case we have a slight slope that can be attributed to the way the loading conditions were imposed. However, we can see that the mean value is around 2.8 Newton per millimeter. What happens if we compare this with the data provided by the manufacturer? We have a slight under prediction. The manufacturer data say that is 4 Newton per millimeter, following the same standard, the STM. However, we should take in account that first, manufacturer data is not always available. Second, our numerical technique or this approach was done using data from literature that was obtained at a different testing speed, so that can justify the difference in the prediction. So in conclusion, we got a good agreement or a good repeatability in the experimental data. In all cases, the failure of the specimen had a quasi-failure, indicating that the adhesive layer failed as it should. Regarding the numerical methodology, we got conservative prediction of the peel strength of the joint, slightly below the one published by the manufacturer. However, it follows the same trend than the experimental data gathered by us. And we have in account that the material properties used correspond to a different strain rate than those from the manufacturer. But despite this, we can say that the proposed methodology can provide a conservative prediction of peel strength, and it can be done using already available data for different adhesive data and different substrate materials. So it can be a good approach for the research. From my side is everything. If there is any question, please feel free.
Thank you for your talk. We haven't time for questions. I have to move to the next presentation. Thank you again.
Thank you.
The next presentation is entitled Interaction of Two Growing Corrosion Pits on the Surface of a Spherical Pressure Vessel, and is presented by Sedova, right? You have to open your microphone, please. No?
Okay, thank you very much. I couldn't find it first time.
I can.
I hope now you can hear me, right?
Perfect, perfect. Okay, you can start.
Okay, thank you very much. Good afternoon, ladies and gentlemen. I will present the results about stress analysis in a spherical pressure vessel with two growing corrosion pits. Short start, pressure vessels are widely used for holding gases and liquids. For gas and oil industry, they are often made from metals. So the corrosion is the important issue for this topic. And one of the most dangerous forms of corrosion is the local corrosion, for example, pitting corrosion. Once appeared, surface defects act as stress concentrators and cause high local stresses and result in acceleration of the destruction of whole structure, and it is really important to access the strengths and reliability of the structure that is under corrosion attack. Pitting corrosion is really hard to predict and to investigate because it's a highly multi-parametrical problem. So despite many authors have investigated the effect of pits on different structures, still a lot of questions has no answers in this field. Because it's really highly multi-parametric. So we made an attempt to study the growth of two corrosion pittings on the outer surface of the spherical spherical pressure vessel, and to analyze the effect of parameters, especially geometrical parameters, and we vary few parameters like initial depths of pittings, sizes of the vessels, and distance between pits. So we consider cylindrical corrosion pits with a hemispherical bottom, and we assume that the pittings grow with time only in the depths. So the cylindrical part of pittings became longer, and the whole geometry still is the same. There are a lot of models of corrosion, how corrosion is accelerates and what is going on with pittings, how do they exactly grow. We consider the mechanochemical corrosion rule, which means that the corrosion rates depend on the stress in the at the surface of the shell. The stress here is the stress at the bottom point of the pitting. So the higher the stress at the point A, the faster is the corrosion process for this pit. At each step, we can calculate the rate of the corrosion for the pit like this, and to recalculate the lengths of the depths of the pitting. We considered few initial geometries for our problem, and here there are sizes and distances between pits and initial depths. We use ANSYS space claim for building geometry and ANSYS workbench to calculate stresses. The whole process was like this. We choose the initial geometry and build it. Then we go to ANSYS workbench and mesh the model and set the boundary conditions and solve the problem and find the stresses at the bottom of the pits. Then we calculate corrosion rate for each pit and calculate the depth of both pits for the next step. Then we build another geometry where the pits are deeper, and go with this circle again and again and again, so that we make the model of growing pittings on the surface of the shell. Firstly, we considered the vessel of these sizes, and we tried to find is there an effect of distance between pits on the their interaction and the growth of it. There are six lines on this graph that I bet you can see them, but believe me, they are there. So one of our important expectations was that we will see actually the sixth curve on this graph, but it didn't happen. So it means that the distance between pits doesn't really affect our corrosion process. And then we decided to consider different distances like this. So, and it didn't work so well for us. So we considered another parameters. We changed the radius of the shell. Because when we consider two pits, imagine that one is starting here and another is starting here, and they both grow into the shell. So when they are deep enough, they will probably interact more if the size of the shell is less. So we reduced the size of the shell and checked what is going on. It helped a little, and it enhanced their interaction between pits. So they start to grow a little bit faster, but not so fast so we could see it like in a graph. But the distribution of the stress field changed a little at the initial geometry, because when we have shallow pits, we have the maximum stresses on the bottom of the pits. But when our pits are growing and became really, really deep, the maximum principal stress has its maximum not in the not at the bottom of the pits, but at the ligament between them. And this little bit changed when we changed the size of the vessel. Here, we for the big vessel, we found that the stress has its maximum on the ligament earlier than for the vessel with reduced sizes. And then they reduced sizes once again, and it enhanced the interaction between pits a little bit more, but still not really big influence we can see of the interaction of those pits to make it really grow faster than single pit on the surface of the same shell. So we had our expectations between about that the distance between pits will have big effect on the stress state of the shell, and another one expectation that the sizes of the shell will have a big effect on the corrosion rate and on the stress state of the vessel too. But it appeared that for our considered parameters, we didn't see it. Though it raised new questions for our further research, and I hope we're going to have it. So, thank you very much for your attention. I don't know whether we have time.
Thank you for your talk. We haven't time for questions. I have to move to the next presentation. The next presentation is entitled An Investigation on the Fatigue Strength of Repair Welded Nodular Cast Iron for heavy sections and is presented by Blaker.
Hello,
Okay.
good evening. Can you see my slides?
Yes, yes.
Perfect, perfect. Thank you so much for your introduction. Yeah, I will talk a little bit about the welding of nodular cast iron related to a research project that we conducted here in Germany at Fraunhofer LBF. My name is Christoph Bleiche, and I'm the head of the division Structural Durability here at Fraunhofer LBF in Darmstadt. The motivation where we came from is depicted here as a component for wind energy, usually manufactured from nodular cast iron, and now and then we might have problems with certain rejects based on material defects that are discovered. And now the question was, is it possible to get rid of those effects and voids and also the rejects of those components when we induce a welding process on a nodular cast iron? And so far we have only insufficient knowledge about this welding process, and there are strong reservations, to be honest, from about those welding processes for wind energy based on the certification bodies for those components. So we decided to investigate the influence of weldings based on two materials, a standard wind energy material, GJS 418 LT. This is the main wind energy material, and also a high silicon grade with a higher tensile strength, 450 megapascal, with a higher silicon content. And both materials, we see here a picture of the cast block. Thickness is here 200 millimeters, and we milled here let me say, as a comparison to the void, we made here a void here in the cast block and welded this area with two different materials, and both materials were welded in a cold welding process. We investigated several welding processes, hot welding, cold welding. The best that worked were cold welding processes for both materials. You see here also given the materials for the welding filler. In the next step, we removed specimens, actual fatigue specimens. You see here again the cast block, and then actual specimens taken from the rim zone, or let me say the heat affected zone near the welding filler. Specimens in the welding filler and also in the base material to make a comparison of the strain and stress based material in the different states to see if we have changes in the microstructure that we need, or also in the fatigue strength that we need for a lifetime assessment. Additionally, we decided to make use an integral specimen comprising the welding filler, the heat affected zone, and the base material to see if we have changing failure modes over those three different areas. You see here the specimen sizes given, and additionally, since we are here only actually on actual specimens, we decided as well to make investigations on bending specimens. There we have also an integral material state, so we have the base material, we have the welding and the heat affected zone, and additionally a stress gradient. And this is what you usually have on components, a stress gradient in notches or under bending loading. So we are here with a bending specimen more or less on the side of, or quite close to the component, to the real component. You see here as an example, a crack that initiated near the heat affected zone and also the fracture surface. Before we made the fatigue tests, we conducted also X-ray analysis to see if we have some welding defects, and actually we had those small pores from the welding process. This is something that you cannot avoid, especially when you're on the construction side and making the welding on not perfect circumstances. We made stress-controlled fatigue investigations until 10 to the power 7 cycles for alternating and tensile loading, and additionally strain-controlled tests under alternating loading. And here on the right side, as an example, the integral actual specimen comprising base material, heat affected zone, and welding filler, and here an extensometer with a gauge length of 50 millimeters. Due to time, I will directly switch to the results. When we look at the cyclic stress strain behavior, it's quite interesting that in the first step, when we look here on the cyclic stabilized material, we see in black the base material here for the 418 LT material. And in addition, in red, this is the heat affected zone. So we see for both materials, on the left side, hand side, the 400, here on the right side, the 450 material, we have more or less no influence on the stress strain behavior coming from the welding process, neither in the base material nor in the heat affected zone. This changes dramatically when we look into integral specimens and also to the welding filler. The welding filler had for the 418 material the highest stress strain curves, but as you see here, a much lower Young's modulus. This is due to the material defects or the small pores that we investigated via the X-ray films here during the investigations. Nevertheless, with those data you get here for both materials and both material welded situations, you are now able to make, let me say, a modeling of your component. When you know the depth of the area that you have to weld, you can assign different stress strain curves to the different areas for a numerical analysis, especially taking into account the different Young's modulus and the different stress strain curves. For the 450 material, we were not able to investigate the integral material state because we had too many problems with the voids and the pores in the welding filler. Nevertheless, you see when we look only on the welding filler, heat affected zone and base material separately on the smaller specimens, there's no difference. So you can assign for the complete component the same the same stress strain curves. Let's switch to the strain life curves. There, it's a bit different. We have again more or less no change in the fatigue strength when we look at the base material and the welding filler. The heat affected zone, but the welding filler and in both cases showed, especially for low cycle fatigue for high elastoplastic strains, a higher strength in comparison to the base material. The integral material state showed the worst results. Nevertheless, when we look on the long run, so in the high cycle fatigue, then they get close to each other. So we have a comparable fatigue behavior when we are looking only on elastoplastic material behavior. And here for the 450 material, this is changed a little bit. We had again comparable results for heat affected zone and base material, but for the welding filler, also in the high cycle fatigue, a little bit higher fatigue strength. So this is the data that we need for numerical analysis from the strain-based side. When we look at the stresses and compare here the different materials, we see that we have, when looking at the actual fatigue specimens on the left hand and the bending specimens on the right hand, we see that we have a strong reduction in fatigue strength, both for actual axle loading and bending loading. And this is getting even worse when we look and starting from the 400 material to the 450/18. So even since we are starting here with a higher strength of the base material, so the 450 material, what you can see here, we are starting here from 170 megapascal for alternating loading in comparison to 160 megapascal. We're getting at the end, due to the welding, to a worse fatigue strength. So in this condition, we are not able to, let me say, improve the fatigue strength in comparison to the 400 material, meaning that at the end, the 450 is not easy to weld. We tried several materials and we were not at the end not that satisfied with the results, and this caused us a bit of headache at the end to compare those materials. The same is when we look from the actual specimens also to the bending specimens. Here the reduction is comparable, around 60–65% reduction in fatigue strength for the data. But you see at least a rest of, let me say, a minimum fatigue strength here for alternating and tensile loading. So data that you can at least use for a comparison for the component design and see if probably the 50 megapascal for alternating loading might be sufficient when you take into account the 450 GJS 450 and a welding made with a Endotech welding filler. Last but not least, some pictures, fractographic investigations. You see here the integral specimen with a fracture in the base material. We had also specimens broken in the pore, on pores in the welding filler, or near at a pore in the welding filler. And yeah, since time is over, last but not least, acknowledgements to the Federal Ministry of Economic Affairs. And thank you so much for your kind attention. And yeah, I do not know if we are open for questions, if we have time. Thank you so much for your attention.
Well, thank you for your talk. We haven't time for questions. I have to move to the next presentation. The next presentation. Thank you again. No time for questions. Yes, we can talk with. You can talk with Professor Blake by chat. Okay.
Thank you.
The next presentation is entitled Modeling of Cracks Healing in Composites by Bridget Zone Grove, and is presented by Perelmutter.
Yes.
Right?
Can you see my screen?
Yes, sure. Can you move?
Yes.
Okay.
May I start? Yes?
Perfect.
Thank you. Good afternoon. Title of my presentation, Modeling of Crack Healing in Composite Materials by Bridget Zone Grove. This presentation can be roughly divided into 3, maybe not equal parts. In the first part, we consider the application of Bridget crack model and thermokinetic theory to modeling crack healing and self-healing. Noted that in the Bridget crack model, the statistic factor is not 0. In the second part, the application on singular integral equation for analysis of stresses in restored bonds and crack Bridget zone formation during crack healing is briefly will be considered, and finally we present some results for numerical modeling. What problem we consider? We consider quasi-static problem for self-healing crack, assuming what the Bridget zone formation start for crack initially without interaction between its faces. In this process, bond stiffness increases with time. Bond formation is considered on the basis for thermal-kinetic model. When modeling target consists in computation analysis of Bridget stress in the computing and in computing of the stress intensity factor, which in this case the main characteristic of crack self-healing efficiency. If the stress intensity factor decrease, the crack healing. We assume what the initial instant of time inside the crack, the process of bond restoring is activated due to some physical process in the material. For example, it may be failure of polymerization in composite or in some cases oxidation reaction inside crack in ceramics. During crack self-healing, the Bridget zone size grows and bond stiffness is increased over time with partial or complete restoration of material mechanical properties. This slide demonstrates Bridget zone stiffness increasing in self-healing process. First case, crack without interaction between surfaces, where for fixed Bridget zone stiffness increasing, and also next step where stiffness also increases on next steps. Next, we consider kinetic of bond formation as the model of crack self-healing. We consider the illustration of bond inside of crack on the basis of kinetic model and assume that the increasing in bonds density between the crack faces with time is described by first-order differential kinetic equation. The solution of this kinetic equation with initial condition gives the dependence of bond density between crack faces over time. During self-healing process, the limiting value of n0 can be attained. Therefore, our calculation stops if the bond density is slightly less than the maximum value of bond density. Next, consider time-dependent bond deformation law. Dependence of bond properties on time are defined by time-dependent bond compliance. It's here. As the bond density increases with time, the bond stiffness in the crack-based zone is growing. Let the stiffness of one molecular bonds K0. Then the effective bond stiffness per unit area of crack-based zone is defined by equation, next equation, where multiple K0 to N is the bond stiffness between crack faces in the based zone. If bond stiffness is the increasing function of time, then the bond compliance is the decreasing function of time. The crack opening due to bonds, in fact, is not opening, it's closing, and opening due to external loading define the total crack opening. By using this relation, I cannot present it here, we can obtain in several steps, which we completely omitted here, the sixth-fold integral differential equation. It's next slide. Equation relative to bond traction in the crack-based zone. The parameter epsilon here define the relative stiffness on based zone. This system is a nonlinear system of second-order Fred-Goldman integral equation and can be solved only numerically. How will we solve this system? For numerical solution, we use a collocation scheme with a quadratic approximation of unknown function. In this case, unknown function is traction of a Bayesian zone. At the calculation start, the size of the storage zone is defined. It's crack Bayesian zone. And following calculation we perform. So at first, the solution integral equation to obtain the bond stresses and crack opening of a crack Bayesian zone. Next, computational stress intensity factor and its model on by the solution integral equation. In fact, it's bond traction. And next, computation bond density and bond compliance of a crack Bayesian zone. A condition for termination of our computation is the criterion of crack self-healing process. It's stop of Bayesian zone formation. In this case, N substring is the average bond density of a Bayesian zone, and here F is healing tolerance parameter because we cannot reach the initial bond density. Next, I show some results very, very short, what we used this non-equal model. First, a crack at the interface between different materials we consider. In case this crack can be treated as a model of crack healing at polymer metal interface. The metal is parameter E1 and E2 it's polymer. We assume that the adhesion layer between material has self-healing ability, and at the initial time of instant, when the crack faces free of concern, some healing process is activated inside the crack, and bond between the crack faces start to build, and formation of crack Bayesian zone is started. We obtain the dependence of stress intensity factor on crack Bayesian zone size for different bond stiffness. Here it's relative bond stiffness. And what this result show us? For bond with relative stiffness about 10, the healing efficiency H restoration if a crack has filled with bonds about the half of its length. It's if about half of crack filled with bonds, next we have no increasing the bond density. An example. In this case, we consider the T-type of Bayesian zone size: 1/4, half of crack, and 3/4 of crack size. For relative bond density 10, what we show on previous results. If only 1/4 of crack filled in with bonds, the self-healing process, we may stop self-healing process because our filling with bonds not give us more efficiency, and 1/4 of crack with bonds is enough for restoring material healing in comparable one size of Bayesian then the D to L about 0.5 and 0.75. And last were some conclusions. The model of crack with Bayesian zone extended to estimate the temporal effect associated with crack self-healing, and the numerical model method has been developed for calculation of Bayesian stress and stress intensity factor time variation during crack segment, and presented some examples which demonstrate the effectiveness of proposed model and the numerical procedure. Thank you for your attention. Thank you very much. If you have some question.
Thank you for your talk. Any questions or comments?
I would like to ask you if you compare your numerical results with experimental ones.
Unfortunately, I haven't any compare with experimental. We do not any experiment, but if I compare some published results, we have a agreement, general agreement, but without any exact comparison.
Okay, thank you.
Thank you again.
Thank you.
The next presentation is entitled Influence of Loading Conditions on GFRP Fatigue Sensitivity Curves, Parameters, and Transition to the Critical States. And is presented by Mugatarov. Right?
Yes, everything is right.
Yes, I can see.
Can you hear me? Can you see my slides?
Yes, you can start.
I hope everything is okay. Thank you very much. Good afternoon, ladies and gentlemen. I'm Artur Mugatarov, a first-year postgraduate student of the Perm National Research Polytechnic University. Also, I'm a research engineer in the Center of Experimental Mechanics. The topic of this work is influence of loading conditions on GFRP fatigue sensitivity curves parameters and transition to critical states. This work is devoted to the problem of mathematical description of fatigue damage accumulation regularities and composite mechanical properties reduction under various loading conditions and reinforcement schemes. Decrease of mechanical properties during cyclic loading is theme which was investigated by many scientists. There are many papers published, but there were many experimental works. Here you can see typical diagrams of tensile strength reduction and damage value for various preliminary cyclic exposure. Previously, authors of this work proposed to plot fatigue sensitivity curves on the left side in the coordinates of preliminary cyclic exposure and small versus fatigue sensitivity coefficient KB, which can be calculated this formula. Three characteristic stages can be defined on the diagram. The first of them, called initiation stage, and third, called aggravation stage, are characterized by fast mechanical properties reduction and high value of accumulated defects. The second one, the stabilization stage, is characterized by it takes place when fatigue efficient decrease slowly and damage accumulation rate is also low. We propose to divide this curve onto these three stages using the points S1 and S2, where damage accumulation rate is equal to 0.3. But such division is conditional and may vary depending on the material and its class, and it can be equal to some parameter delta. Here shown some approximate formulas of fatigue sensitivity curves. The first one is based on two-parameter Weibull law of probability distribution. The second is based on beta distribution. The third model was proposed by Mao and Mahadevan. The first pair of models requires definition of two parameters. It's lambda and kappa, or alpha and beta, and these models was proposed by us. Last model requires three parameters definition. Each of parameters, of course, in general case, depends on loading conditions, temperature, stress state of material, etc. Previously obtained fatigue sensitivity curve was approximated using these three models. You can see fatigue sensitivity curve and damage accumulation rate curve on this slide. The model which was proposed by Mao and Mahadevan has the best fit to the experimental data. However, it shows very slow mechanical properties decrease on the aggravation stage, and it seems to be implausible. The beta distribution and the Weibull law-based model are very similar, so all the other experimental data was approximated using only Weibull law-based model. First, we investigated maximum stress value during the cycle influence. GFRP specimens were tested under various maximum normal stress values equal to 0.4, 0.5, and 0.6. Fatigue sensitivity curve and damage accumulation rate curves were plotted. The dependencies of the model parameters on the maximum stress value during the cycle are nonlinear and non-monotonic, and we can see that low value of stresses led to fast reduction of mechanical properties on the initiation stage, but it makes stabilization stage long, and damage accumulation rate is very low. Then we investigated temperature influence and room temperature and under 120 degrees temperature. High influence of the temperature on the fatigue sensitivity was found out. High temperature during tests led to longer duration of the stabilization curve and late completion of this stage with the low damage accumulation rate. The last fatigue sensitivity curves parameters also depends on reinforcement scheme of the composite. It was discovered that ±45 scheme, this one, the red line, has long stabilization stage and low strength decrease. It means that cross-reinforced glass fiber reinforced plastic shear strength isn't sensitive to preliminary cyclic loading at all. Here are some conclusions of the work. Experimental data of the GFRP strength decrease under various loading conditions and reinforcement schemes was obtained. Approximation of experimental data using various models was carried out. The significant influence of the loading conditions on composite reinforcement scheme on the fatigue sensitivity and the damage accumulation rate curves was revealed. And we plan further modification of these models for the usage under various loading conditions. Thank you very much for your attention. I'm ready to answer your questions.
Thank you for your talk. Any questions or comments? I have just a curiosity. Which loading ratio have you considered in your investigation?
We had the loading ratio, I mean asymmetry coefficient during the cycle. Yes. We have it 0.1 to avoid the compression during the cycle.
Okay, thank you again. The last presentation is entitled Ultimate Strength Value of Stiffnet Panels Designs under Initial Displacement and Applied Pressure, Finite Element Analysis versus IACS CSR, and is presented by Lutfi.
Yes,
Right?
it's me. Yes.
Okay. Can you share your screen, please?
I see my screen. Hello.
You can start.
Okay. Good evening, ladies and gentlemen. My name is Yogi Muhammad Lutfi from 11 Maret University, Indonesia. I want to present our research entitled is Ultimate Strength Value of Stiffener Panel Designed under Initial Displacement and Applied Pressure, Finite Element Analysis comparison with IGF27. This presentation includes introduction, configuration of finite element analysis, and then result and discussion, and the last is conclusion. Number one, introduction. See, transportation widely used due to its huge trading volume and the low cost of ship transportation. The safety effect of structural assessment of stiffener panel and ship structure under different loading scenario has been studied. However, in report by the European Marine Safety Agency during 2014 until 2020, there were 1,500 accidents on EU flag vessel, and of all these accidents, 58 were caused by hull failure. The purpose of this research is structural evaluation of stiffener panel, subject to transfer and lateral pressure acting on the bottom and side plates. Number two, configuration of the finite element analysis. Hull reference model, as we can see, figure 1, hull grider section, cross-section of hull carrier, point A 3D model, and point B is 2D model ISSC 2000. And then the hull carrier has 30 and 24 stiffener panel. The selection of the model for the study include the stiffener number 2 and 3 according to figure number 1 in this red box. And then geometrical modeling, and the difference between the two models in thickness and flank. Thickness, flank, and height web, as you can see in figure number 2. And then element discretion in this work is set to 25 millimeter in size on the overall geometry like figure 3. And then boundary condition in this modeling can be seen in figure 4. Applied loading scheme, as you can see, figure 5 is panel illustration. Point A, it is a schematic 3D model of an overall panel, and point B, the 3D model in the current finite element analysis with the applied loadings. The applied loading scheme, they are in two steps. Step number one is pressure 0.16 megapascal as lateral and transversal load. And then step number two, impulse displacement 5 millimeter as axial compression. Number three, result and discussion. Design final geometry. After simulation, as you can see in figure 6, step 0.0, the model before applied the load. Then the result for the initial step or 2.0 are obtained in figure number 7. The model only accepts the pressure force without axial compression. The force is obtained from the pressure under the plate and side of the plate. As the result, the middle part of the model has the high stress. After adding axial compression, the stress obtained by the model will be higher at each step. At step 2.8, experience the ultimate strength of the model. The model reached ultimate strength so that the strength of the model is at maximum level. When the simulation increment is continued, the model will distribute its stress until it cannot be endured. Based on the result present in figure 8, it can be concluded that the stress in model focus on the center, which is affected by axial compression. Then there are bends in the model, both from the plate, web, and flank. This was influenced by the high stress that the model could not withstand. This phenomenon is called column buckling. After analyzing its increment, the result of the light and heavy model as present in figure 9 and figure 10. Two conditions are given, pressure and without pressure. It is found that there is a slight difference in the ultimate strength between the two conditions, which specifically occurred in the stress range 250 megapascal until 300 megapascal, and strength 0.001 and 0.002. The estimation of this difference is not higher than 5% of overall stress. The structural behavior observed in post-ultimate strength was achieved as closer 0.004. The like model with and without pressure, put the stress was fallen to approximately 190 megapascal. An opposite tendency is recorded from the heavy model in figure 10, in which after the ultimate point was achieved, the stress behavior was found to decline as the strength approached strength 0.004. The stress of both the heavy model with and without pressure was put higher than 200 megapascal. Even though the model without, it can be taken as an initial conclusion that the pressure effect is lesser in the proposed heavy model. Then comparison of the finite element result and IGF regulation. This is a table comparison. Additional loading has a negative effect on the ultimate strength value, reduce the ultimate strength value. The decreasing ultimate strength value is in line with small inertia of the area of the model. Reduction of the ultimate strength record in the rank 4 until 7% for model without pressure in finite element simulation, and 1.5% for the calculation using IGF27 regulation. Number 4, conclusion. In this research, the ultimate strength calculation was carried out on a design stiffener panel as an idealization of the full carrier structure. The model is divided into two, namely the light model and the heavy model. The choice of the model refers to the location of stiffener panel, the sides and the bottom of the hull. The ultimate strength calculation is carried out by based on IGF 2022, under buckling condition, there are two loading pressure with value of 0.16 megapascal and imposed displacement on both sides of the web of 5 millimeter. The addition of pressure has a negative effect on the ultimate strength, or can reduce the strength of the model. The smaller the inertia of area, the lower the ultimate strength. And then the ultimate strength simulation result saw a decrease from the IGSR 2020 ultimate strength. Thank you for your attention.
Thank you for your talk. Any questions or comments?
Well, I'd like to ask you, which parameters have you employed for convergence in your finite element model?
The parameter used for the convergence analysis. Convergence analysis.
Okay. In parameter in the finite element, this is geometrical, this is thickness flank, and then height web, the difference of two model, and then the meshing of model, it is 25 millimeter, and then the boundary condition in figure 4.
Okay, thank you. Thank you again. This session is now finished. I would like to thank all the speakers and the participants, and I hope all of you have enjoyed. And see you tomorrow. Bye-bye.
Goodbye.